Hey guys, it's Chili here, and let me tell you, I am pumped because I've got a bit of a treat for you today. I'm starting a new series, and that series is going to be, well, I guess you can tell if you're looking at the screen right now, it's all about SSE and optimizing code. Well, it's not all about SSE. I'll talk about some other considerations along the way, but it's going to be mostly about SSE because SSE is going to, you can make routines that are so fast it'll blow your fucking mind. So I want to share this with the world at general. The people must know about the SSE revolution. Some of you might be wondering about hugs. Have I canceled that series? No, I have not. I've gotten other things have come up. I've taken up my time, and my interests have kind of been distracted for a while, but I've definitely not canceled. I fully intend on finishing that series. But, for the moment, I want to do something else, and I could just wait and start up just make no tutorials until I'm ready to start Hugs again, but I figure, why not start a second series running parallel to Hugs, and that way I can still keep the videos coming. This series is going to run parallel to the Hugs series. And to be honest, I was actually planning on covering this topic throughout the Hugs series as like a part of it, but the topic is too big to form just a small part of one series. It deserves its own thing. It is its own thing. You are your own thing, SSE. You do you. So we're going to be doing it in its own series. I've checked YouTube, and I've found that there aren't too many goods. Well, I shouldn't say that. That's slanderous. But I can't find too much information on SSE programming. So now's my time to shine. I've found my niche again. So yeah, I guess I'll just get into it now. So what is SSE? Well, it's an acronym. It stands for Super Strong Erection, because that's what I get whenever I think about programming in SSE. And when I'm actually programming, you don't even want to know what's happening. It involves liquids. Anyways, that's not what it means. It stands for Streaming SIMD Extensions. Yes, it's an acronym within an acronym. BBBQ. The extra B stands for BYOBB. What does that B stand for? Oh, that's a typo. So, streaming doesn't matter. Extensions doesn't matter. The important part of this name is the SIMD part. The acronym within an acronym. And what it stands for is Single Instruction Multiple Data. That's the technology paradigm, the programming paradigm that is represented in this instruction set. And it allows you, the idea is to perform multiple operations in a single instruction. Single instruction, so one operation, but performed on multiple data points. So instead of performing one multiply, you perform 4 at a time, or 8 at a time, or 16 at a time. And obviously that's going to be way faster. If you're performing 4 times as many operations, you're working 4 times faster. Seems obvious. Well, quickly to overview, SSE, in the processor, it has its own set of registers. They're called, XMM0 through XMM7. Now, if you generate your code in 64-bit mode, then you actually get 0 through 15. You get double the amount of registers, but we won't worry about that right now. And these registers, their width is 128 bits. That's fucking wide. Think about a 128-bit number. That's like 34 with like tons of zeros after it. I can't remember how many. I think like 37 zeros or something like that. Something stupid like that. Anyways, it's a fucking big number. So you might be asking yourself, well, Chili, why do I need to program or to code with 128-bit numbers? That doesn't help me. I'm not going to need to store a value that high. I'm never going to use that whole dynamic range. And no, you're not. Of course not. Like the move from 32 bits to 64 bits, like some people would say, well, you're doubling your bits, you're going to double your speed. That's not how it works. I mean, most programs don't really need the extra 64 bits. The reason why we have moved to 64 bits mostly is just to increase our memory space more than because we need 64-bit width of instructions. So moving to 128-bit is obviously not going to benefit any but the most niche of applications. But that's not what we do with this 128-bit register. Oh no. What we do is we pack values into our register. So let me show you something here. So this thing that I'm bringing up here represents a 128-bit XMM register. And it's divided up into 8-bit regions, each region holding an 8-bit value, a byte. And we can perform operations to add each byte separately between two 128-bit registers. So we can add 16 bytes to 16 other bytes in a single clock cycle. And that is hella fast. Just one example of how SIMD works. So you got two registers and you're adding vertically. Almost all your operations that you're going to be doing are vertical. So you want to add, so you add the one in the, this is the high and this is the low end of the register. This would be bit 0 and this would be bit 127 at the top here. You're adding each byte to its corresponding byte in the second register. First register to second register. In general, if you want to add, like, I want to add diagonally, or I want to add crosswise like this, there's no easy way to do it. You're going to have to do that in multiple operations. So with one of the big battles in SSE programming is getting your data lined up properly. You really have to think of how you're organizing your data to minimize all the shuffling around you have to do. But this is the basic concept. You pack data types, multiple types of the same data into registers, and then you process them together. They also, they have to be, I think all the instructions require the data to be the same. So it has to be all bytes or all words or all single floating points or all double floats. You can't have I'll have a double word here, and then I'll have a word, and then a word, and then I'll have a byte, and then I'll have a word, and then I'll have a float, and then a byte. That's not how it works. It's got to be all bytes or all floats. That's what you get. I guess I'll show you the code that we're going to be working with. This is going to be up on GitHub. It is up on GitHub, and I will put the link in the description so you can pull this off of GitHub. And yeah, you clone it, I think is the term. I don't know. Whatever. Clone this and you can follow along or not. You can just watch me. It doesn't matter. Very basic framework here we have. Got some images we're going to be using. Here's a log file that is going to store benchmarking data. Because rule number 1 of optimization is always benchmark. Because you'll make assumptions. You'll be like, I believe this way will make my code faster, and you'll code it up. And then you'll actually benchmark it, and you find out that no, the compiler was doing it faster all along. So rule number one is benchmark everything. Assume nothing about the performance impact of your changes. Always benchmark. That's rule number one. So most of our work is going to be in the surface class. I've added a shit ton here of functions, and they're basically, for the most part, they're filters, full screen filters, and later on we're going to have some like draw rectangle and blit functions, but lots of filters, lots of blending, and this is going to be what we use to practice SSE. It's a perfect playground to wet our feet, as it were. The thing about SSE is it works best when you have a lot of data. You need lots of data. And then the data has to all be contiguous in memory. It can't be all over here and there, and that's bullshit. It's got to be all lined up, and it has to be wow. It's got to be homogeneous. Homo. Yes, homo. Just think, when you think SSE, think yes, homo. You want your data all to be the same layout. And pixels or graphics data, surfaces, they fill all these requirements. There's tons of pixels in a back buffer. They're all contiguous in memory, and they're homogeneous. They follow the same ARGB pattern throughout memory, or BGRA, depending on how you're lining up your bytes. So that's why I chose this topic for the first series of videos on SSE. So I've got a bunch of functions here. And the first one we're going to look at is the simplest thing you could think to do on a whole surface, and that's just clear the surface. Set it all to zeros. So let's bench this. Let's see how long it takes to clear the whole surface. Mind that my numbers are going to be probably a little off because I'm running my my capture software at the same time, but shouldn't be off by too much. And of course, it does not matter because you're going to have different computers than me either, so it's not like you're going to be able to compare yours directly to mine. So what we want to do is we want to go clear. And we'll build that. And then we'll run it without debugging. And we'll get a black screen like this. I've set the size of the back buffer for this framework to 1280 by 720p. So it's a little bigger than the other stuff we've been doing in the tutorials. Let's look at the log file. We can just click it here in our resources, and we see it takes about 100 microseconds. These are in units of milliseconds, so 0.1 milliseconds, so 100 microseconds to clear the entire back buffer. All right, I guess that's okay. We don't really have anything to compare that to, so sure, I'll buy it. Now let's take a look at the SSE version of clear. This one just calls memset, so we don't really know how it's doing it. It's just doing it somehow. The SSE I've actually coded myself. And it works like this. Geez. All right, so before I talk about this, there's one other thing I want to talk about. Let's take a look at another function here called fill slow. If you look at memset, the parameter here, the value that you fill into memory, it says it's an int, but in actuality, memset sets bytes. So this value here, it's not going to set 4 bytes at a time. It's setting 1 byte at a time. So for example, memset 0 is exactly the same as memset, for example, 256. Build that. Still black, right? Or I could go memset, let's see here, I'm trying to think of a color that has 0 blue, and what does red and green make? Does that make yellow? I believe it makes yellow. So if we go yellow, the low byte should be 0. And in fact, yellow gives us a black screen. Whereas if I went blue, I should get a white screen. Because the low byte is going to be FF. And when you fill the entire thing with FF, you'll get white. So memset is okay for setting to black or white or any gray value, really. But if we want to set to any arbitrary color, we can't use memset. So let's write our own filling function that will fill the memory with double words and not bytes. And what we would probably come up with is something like this. Just a simple nested loop, put pixel. Now you might have a premonition about how the performance of this function is going to be based on its name. But let's run it anyways. So fill slow. Remember, filling with bytes, 100 microseconds. Fill slow gives us 630 microseconds. That's over 6 times slower. And remember, we're still filling the same amount of memory. We're just filling it in chunks of double word instead of chunks of byte. So that's not really that good. I mean, it's pretty terrible when you think about it. And you might be saying, well, Chili, you're putting a function call inside there. It has to jump to that function for every single pixel. And true, if that were the case, it would slow us down, but this put pixel is actually being inlined in here. If I were to replace this put pixel with the call with the body of put pixel, now let's just go in here. Where's put pixel? Here it is. So let me just, for argument's sake, replace the function call with, where is it? This way. Replace the function call with the actual statement that the function contains. And we'll run. Stop. And look at the log file. Still the same result. No change whatsoever. Because, of course, that function call was being inlined. The problem here is, well, let me just go back. Let me replace this. Every pixel, we have to calculate the address of the pixel to fill. So we've got to take y, multiply it by some constant, then add x, then add that result to the address of the beginning of the buffer. And then we can move our data. And that's slow. So what we do instead, the alternative is, instead of looping on indexes, we loop on pointers. So we initialize our pointer to the beginning of the buffer, and we also initialize an end pointer to the pixel or to the byte that follows the last byte in the buffer. And we keep looping, we keep incrementing the pointer until the pointer reaches the end of the buffer. And because we do this, we don't have to calculate the address every iteration. The address already exists. The address is just the loop variable. They are one and the same. So if we replace fill slow with plain old fill, build this motherfucker again, and same result, of course, green screen. Look at the log file, and we're back down to 100 microseconds, which makes sense when you think about it. Because, yeah, you're still filling the same amount of memory. So why wouldn't you have the same time taken? And that's what you get. So the moral of this story, I believe, is obvious, and that is, especially when you have a loop body that doesn't do much work, you want to avoid looping on indices, and you want to loop on pointers, because this overhead can actually become quite large in comparison to the operation you're performing. So that's my optimization tip number one, particularly for tight loops that run a lot. Loop on pointers. And now that enables me to talk about the SSE implementation of clear. Because as you notice here, again, we're looping on variables. We're not looping on an index or indices. We're looping on one pointer. So where to start? First of all, like I said, SSE works with 128-bit values, or smaller values packed into a 128-bit register. So to use SSE, you need a new data type. And that data type is the __ M128. There are two versions. There's a version with an I and a version without an I. The version without the I is for floating point values, so singles or doubles. The version with an I is for integer values or just bit values. So we're going to be making a lot of these. And of course, we have a pointer to that. So we're going to cast our buffer pointer, which is a pointer to color, and we're going to cast that to a M128. And again, with the beginning and the end. If you don't know what this is just another way of casting. I could have easily just written the C style cast M128, and it would work exactly the same, no problems. But sometimes I feel like being a little fancy, using the C++ style casting. But it is long as fuck. But what's done is done. So, what are we doing in this operation here, in this routine? First, we're creating a 128-bit variable, and basically these things end up becoming registers. So the compiler just turns them into registers in memory in most cases. Unless you have so much that it can't fit in all the registers, and then you overflow your registers, you get register thrashing, which is not good. But in general, these are just registers. So we create an XMM register and we fill it with 0. And then in our loop, we store that into the memory pointed to by I. So we're storing 16 bytes at a time, or 4 pixels at a time, with this operation here. So 4 pixels at a time, that should be pretty damn fast, right? Well, let's give it a shot. So we'll go clear SSE. And we don't need a parameter. We'll run her for a second. We get the black screen as expected, and looking at our data, well, we are actually like 28% slower, or maybe 25%-ish, I don't know, slower than the case when we just called memset. So memset is actually faster. So you might be wondering, well, geez, if we're moving 4 pixels at a time with SSE, what is memset doing that's so goddamn fast? And, well, let's take a look at that. An important part of optimizing, especially optimizing with SSE, in my experience, is inspecting the actual instructions that the compiler emits. So we're going to try that right now. We're going to set a breakpoint, and we're going to start with the debugger. And the first thing you notice is the breakpoint isn't being triggered. And you might say to yourself, well, geez, Chili, I could have told you that breakpoint was going to be triggered. You're not in debug mode. But we don't want to debug in debug mode, as counterintuitive as that sounds, because debug doesn't generate the same code, doesn't emit the same instructions as release. It emits way slower, lots of safety and checks and all sorts of junk that it inserts in there, all sorts of optimizations that it doesn't undergo or undertake. So we want to inspect the actual generated instructions in release mode, and we can do it. But the problem is, the reason why this isn't being triggered isn't because we're in release mode. It's because this function doesn't actually exist. Or to be precise, it's being inlined. So this function is going to be inlined into here. Oh, wait. Okay. Well, first one reason why the breakpoint might not have been triggered is because we weren't actually calling the function. So I'm going to call the function now. And again, the breakpoint isn't being triggered. So the reason is because that function is being inlined in here, and that is probably the composed frame is probably being inlined in Go as well. So what we could do is set a breakpoint at Go and try to trap it from there, or the method I prefer is just to tell the compiler, don't inline this function. So we go decal spec no inline. And that tells the compiler, don't inline this, dude. Just leave it, man. Just call it like a function. Be cool, bro. So if we start debugging now, we trigger the breakpoint. And it is at this point that we go to disassembly. We don't have the source for memset, so we can't step into it. We just have to go to disassembly. And we step, and when we hit call, we want to step into. And that'll jump to memset. And then we got another jump for whatever reason. I don't know. It's a thunk or something. I don't know what it is. I don't know and I don't care. We got tests. Some stuff. More tests. More jumps. Move. Push. Move. And here is where the magic happens. Rep stos. So the stos instruction, store string, is an instruction that has actually existed in x86 since, like, I believe the beginning of x86. I'm not 100% sure, but it's been there for a long time. Probably since, like, the inception of the chip. And what it does is this one instruction will fill the entire back buffer in a single instruction. And you might say that's super fast, Chili, but it doesn't do it all at once, obviously. It enters a hardware loop in the CPU. It stops fetching instructions, and it just fires the specified byte value into memory. So you have to set up your registers. I believe one of the registers, probably EDI, will be... I'm guessing EDI is probably the count. But I could be wrong. Oh, maybe C, because C is count, right? So probably ECX is the count. That's how many bytes you want to move. And EDI maybe is the value, the data, which would be 0. Is it 0 here? We can actually look. No, it's not 0. Okay, well, I don't know. I don't know which registers hold what values, but you set your registers up with the data that you want to fill and the count, and then you execute the instruction, and the CPU enters a hardware loop where it decrements the counter and fills in the data in the pointer. Yeah, you've got to also set the pointer. You got to set the data, you've got to set the pointer to the start address, and you got to set the counter of how many bytes to fill. And it uses that information to fill out a block of memory. Now, the thing about rep stos is it was an instruction intended for exactly the purpose that it's being used here, which is to fill a block or a string in memory with a single value. But with the advent of MMX and later on SSE, where you could move 64-bit data and then 128 bits of data in one instruction, it turns out that rep-stos was actually slower and it went into disuse. In a lot of situations, it was a lot faster to use SSE, for example, to move your data. However, it turns out that Intel made a change starting with, particularly with, where is it? Ivy Bridge, and it's called the Enhanced Rep Move SB and STOS B operation. So when you're using the rep operation with the STOS, particularly for bytes, you get high performance. Basically, the CPU enters like a whole different mode, and it moves data at the most efficient way possible. And that's good. So what's actually happening in memset, remember those tests that were at the beginning, it actually gets the capabilities of the CPU. It checks to see if those enhanced rep-stos capabilities exist, and if so, it uses that. And if they don't exist, then it defaults to SSE. But if SSE doesn't exist, then it tries MMX, and it probably tries a bunch of other things, and a whole bunch of special cases for alignment, and there's lots of fun stuff in memset. But the fact of the matter is, we're not going to beat instruction that has been highly tuned to do exactly what we want to do. Not even with SSE, although we do come close. Now, the surprising thing is, if you remember, I'm just going to get rid of this no one line now. If you remember, Phil got the exact same performance as memset, even though Phil does not use rep-stos. We can confirm that. We go decal spec no inline, and we can confirm. Just make sure I don't make the same mistake again here. We'll go Phil C. Build that mother. And we'll start. I believe we want to probably set a breakpoint here. And we'll start with the debugger here. We'll inspect the disassembly. And we see that our loop, we're going to add. So this is incrementing the pointer, comparing it with the end, jumping to E3, which is over here. So what this loop is actually doing is it's loading from memory the value of C, and then it's storing that into the address pointed to by EAX, which is I in this case. And this is getting the exact same performance as rep-stos, which is a single instruction which puts the CPU into a crazy memory filling frenzy mode. And that doesn't seem right, especially this code doesn't even seem like a good idea. I don't know why it's loading every iteration. It could just load ECX once and then fill that into memory. But anyways, don't worry about that, because obviously it doesn't make a difference. It's getting the exact same performance. And I don't know why, but I have an idea. And I believe it might have something to do with the loop stream detector. What this does is it detects small loops that fit in the instruction queue, and it locks them down so that it doesn't have to keep reading instructions from memory. And that can, allow shit to run faster, ostensibly. And also, I believe that perhaps the micro ops that this translates to might be detected as basically wanting to do the same thing as rep-stos, and it might just put the CPU in the same mode that rep-stos does. But I don't know. That's 100% conjecture on my part. At any rate, that's what that is. So the moral of this story is, like I said before, you can write code that is slower than what you already had before you started optimizing. And so it's always important to benchmark everything. Because as we see in this case, we've actually done more harm than good by writing our own SSE clear. And SSE fill is the same story. But before I talk, well, let's talk about SSE fill as well. So fill by itself, we've got fill in here. Let's run it. And we'll take a look at the performance. Right, 100 microseconds. And if we go fill SSE, I believe we can all guess what we're going to get here. Take a look at that and look at the log file. 127 microseconds. So, same story as with clear. We can do better with just a straight C function, even without relying on repstos. So, what was I going to say? I don't know. Just make sure you benchmark everything. All right, so now I'm going to shift gears a little bit. And I'm going to talk about just how we write some SSE code. You may notice some difference from standard C code. Let's dive right in. So the first thing you need to do if you want to write code with SSE is you need to include this include file, immintrain.h. That's, I think, the most recent one. That'll give you all the intrinsic functions up until avx2, I think. And also maybe fuse, multiply, add. I don't know. Anyways, you need to include this. And that'll give you access to these functions. They're called intrinsic functions. They're a little different than your standard functions. They don't get called ever. So they don't ever have their own function body. They are always inlined. And they generally all, well, there's a few exceptions, but most of them map to a single instruction. A single SSE instruction has a single intrinsic that is associated with it. The set functions are a little different, but we'll get into that later. So set 0 is an intrinsic that sets an M128 value to 0. So it sets all 128 bits to 0. The mnemonic here is multimedia, probably, MM. That prefix, M's prefix basically everything, SSE, MMX, and AVX. That's just the lingo. Then set 0, pretty self-explanatory. SI is single integer, and then 128 bits. So it's just treating this value as a 128-bit integer, setting it to 0, which means setting all the bits to 0. And store, the store intrinsic here, will emit I believe emits a move DQA instruction, which is move double quad aligned. And it just moves the value of 0 into the memory pointed at by I, moving 16 bytes at once. So, I guess I can probably be a good idea just to look at the disassembly of this. So we'll go clear SSE. And yeah, I'm moving quite slow at the beginning here, but we'll definitely speed it up as we become familiar with the basics of SSE programming. But for now, we're gonna take it slow. So just sit back, relax, and let the code wash over you. Say decal spec no inline. So we're gonna Like to continue. No. What is your problem, dog? Buffer undefined. Does not take, okay. Well, I can fix this. I'm not sure about the other error, because that was just bullshit anyways, so doesn't matter. And we'll go to our disassembly. And so we see our code here. And what do we got? We got some setup stuff for the loop. Here is where the register that corresponds to 0 is set to 0. It's just exclusively ORed with itself, which is the same as setting a register to 0. And what else we got? Here is where the store SI128 happens. Move double quad aligned and moves the value in XMM0, which has been set to 0, and it moves that value into memory here. The memory pointed at by EAX. So EAX corresponds to our loop I, and so on and so forth. Now, one question you might ask is, okay, I understand move, I understand double quad, that's just 16 bytes. What is aligned? What does that mean? It means that we have to be moving data into addresses that are aligned to the size of an XMM register. We have to be accessing, in this case, storing at addresses that are multiples of 16. For addresses not a multiple of 16, we are going to be fucked. So let's try that out. So we're going to start our pointer. Instead of starting at the beginning of buffer, it's going to start at the buffer plus 1. So that's going to be 4 bytes into the buffer. So if our buffer started at 0, our I is going to start at address 4. And just so that we don't run past the end of our buffer, we're going to subtract 1 from here so that we don't, overrun our buffer. And let's see what this does for our complexion. We don't want to trap that. And we get an unhandled exception, access violation. And it's not going to help us. It's not going to tell us where the error was, but it's obviously right here. And that's because we tried to store to an improperly aligned address. So you have to make sure all your accesses are aligned. It's not a big problem for us now, but it becomes a pain in the ass later on. But we'll talk about that bridge when we cross it. There is one issue that we do have to cover, though. So we can make sure that we are properly aligned within the buffer. We start on, the first byte of the buffer, byte 0 in the buffer, and then we increment the address by 16 every time, right? Incrementing a pointer increments by the size of the data that pointer points to. So incrementing I increments by 16. So we're always going to be accessing 16-byte aligned addresses within the buffer. However, how do we know that the memory that we were allocated, the buffer block, starts at a 16-byte aligned boundary? We can't be guaranteed that, can we? Now, I've never had a problem in my personal experience with my setup with new. So new has always given me a properly aligned memory address. However, malloc has not. So I don't know the rules. I don't know if new is going to give you a 16-byte aligned in all operating systems or for all compilers. I suspect it varies depending on what the compiler is, possibly on what the operating system is as well. And it's not good to leave that just to chance. It'll probably work, but maybe it won't work for some people. That's not good. So what we're going to do is we're going to replace this call with aligned malloc. Size of color times height times pixel pitch. And the alignment is going to be 16 byte. So aligned malloc will guarantee that the memory block that is allocated starts aligned to, well, in this case, a 16 byte boundary. Very important. So we're going to cast this to color. And I'm not going to use C++ style casts at this moment because time is of the essence. I know you're all important people. You got things to do, places to go, people to see, things to see, people to do, places to do. And if we do aligned malloc, we can't do a delete. That'll fuck us up. But we should do an aligned free. I don't know why you need to use aligned free. Like, why wouldn't free work? In actuality, I've used free and it worked fine, but whatever. Might as well use aligned free because it exists. So you should be using aligned malloc, although in my experience, new has never crossed me yet. But I still view it with a jaundiced eye. So I use aligned malloc. And that guarantees me alignment. That guarantees me alignment. That was a horrible accent. It was a horrible attempt at an Irish accent. I don't even know why I tried. All right, so the difference between fill SSE, I'm just completely going off in a new direction now, but the difference between this and this is only that in this one we set the register to 0, and in this one we're setting our register to our color. So we use the intrinsic set1 EPI 32. So what set1 means is it means set all of the values packed into this register to one single value, and the type of packing that we specify here is with the thing that follows. So EPI stands for extended packed integer. Forget about the extended thing. It's extended relative to MMX, which is like that's your granddad's technology. That's what that is. So forget about the extended. It doesn't mean anything anymore. But packed integer means we're working with we're treating the register as a register containing packed integers of size 32, which by coincidence, or not coincidence in this case, is the same size as a pixel. So we're setting the 4 double words in this register to a single value, which is C. All right, and that is the only difference between the clear and the fill functions for SSE. And I think this is where I would like to end this episode. You might be saying, well, Chili, shit, I don't really see the big deal about SSE here. I mean, you're fucking slower than your standard C functions. And you're not wrong for this case, but we've only scratched the very surface. We've only gotten the tip in, just the tip. And where SSE really starts to shine is when we start doing some processing. After all we're doing here is just storing data. So once we get some actual processing going, that's where you're going to see SSE shine, baby. But that's for the next episode. I got to leave you on a little cliffhanger. But I think we covered quite a few interesting topics here. Just in general optimization, not even considering SSE. So look forward to next episode. I'm Chili. Peace the fuck out. All right, it's Chili here. Welcome back to the SSE optimization series. And today we are going to actually get down to some processing. Now, the first filter, the first effect that we are going to be tackling is a fade effect, fading to black, which is simply just blending whatever's on the back buffer with the color black. Now, we've done blending before. We've done it in alpha blending, and we've also tackled the same concept when we were texturing triangles. So let's just do a quick review of that though. Now, alpha blending in general, is just a linear interpolation between two values, where if alpha is equal to 0, right, you're going to get all color 2, and if alpha is equal to 1, you're going to get all color 1. And if alpha is equal to 0.5, you're going to get an equal blend between the two. So what we want to do here is we want to reformulate this in such a way that we can do it with just all integer math. And this works because, of course, we're multiplying C1 by the fraction of alpha over 255. And that fraction converted to decimal will be a fraction between 0 and 1. Of course, you have to be mindful that the order of operation has to be multiply and then divide, because if you divide first and multiply, you're going to get all fucked up. Now we're going to make one more slight adjustment. Dividing is a slow operation, and if we can avoid it, that would make our lives much easier. If we instead of dividing by 255, if we divide by 256, this will make the operation a hell of a lot faster. Because dividing by a power of 2, right, 256 is just 2 to the 8. So dividing by a power of 2 can be implemented by bit shifting. Shifting to the right 8-bit positions is equivalent to dividing by 256. So by altering our formula slightly, we're going to be off by a very little bit. We're probably going to be off by about 0.4%, give or take. We're introducing a bit of error into our calculation. But by making this slight trade-off, compromise, I guess, we can increase our processing speed quite a bit. And I'll show you how that works out later on. Now, when we're fading, C2 is equal to 0, so this gets canceled out. Kind of forgot to mention that. I hope it was obvious. If not, well, I guess you know now, because I just told you. So we're going to do it first with the non-optimized, just standard C, and then afterwards we're going to see how it looks in C or in SSE. So here's a standard fade here. We load a color, and then we do what I just showed you on the whiteboard. We multiply by alpha, and we divide by 256. Now, I know I told you that dividing is slow and we'd rather right shift, but the compiler is smart enough to know that if you're dividing by 256, it can just do a right shift and save a lot of instruction. Or a lot of clock cycles, I should say. So let's build this. We're gonna, well, we don't want that in there. So I believe it was fade, and we need an alpha value, so we're gonna use alpha. Now, alpha in this test bench is controlled by the mouse wheel, so we can control our alpha value using the mouse wheel. And we'll build this, and I'll make sure we're in release mode, and then I'll run the motherfucker. So here we go. I can use the mouse wheel. I can fade in, go too far, and go roll over the other way and go back to black. And so that works fine. And let's look at our execution time. So holy shit, it takes about 5 milliseconds, 5,000 microseconds to fade the screen, compared to 100 microseconds to fill it. So 50 times slower. Yeah, it's 50 times increase over just a standard move. Seems pretty bad. Now I just want to do one short double underscore decal spec, no inline. I just want to show you guys, make sure that this is actually being optimized here. So we're going to run that. And we're going to go to the disassembly. And you'll see down here, once you get into the body of the loop, that we are shifting right. This is shift algebraic right by 8. So we are shifting right a bunch by 8. So that's where our division. There is no division. There's multiplication. There's no division instruction being called. It's all shifting. So we can see that the optimization is being carried out, but we're still goddamn slow. And I found when I did this, I was like, wow, that's really shitty. So what I did was I created another version, and this version, it unpacks using the what do you call it? What is it called? The union. So in colors here, I define color as a union between basically just a standard unsigned integer and a structure broken down into the character components of the colors, the different channels. And you can refer to this data either as a single integer or as one of the 8-bit channel components. So using that, I can basically unpack the data, perform the operation, and then I use the constructor for color to repack it. And I figure this is very succinct. This is a very nice, very elegant way of writing the code. But what would happen if we do it the old-fashioned way? And we unpack by shifting and masking out the top bits. So masking by FF will clear out everything in the higher bits. Then multiplying by A. And then right shifting by 8. I could just put divide by 256, but I figured since we're writing everything here out in bitwise operators, might as well be consistent. And in the end, then shifting the components back into their positions and bitwise ORing them all together. So, like, we would expect for a really good compiler, it should be able to generate identical code for these two identical operations. However, if we actually run the motherfucker, remember that just the standard fade was 5 milliseconds. Now let's run this motherfucker with fade shift. So here we go. Modify the alpha value a little bit there, and let's take a look. And we see that now we are at 1.29 milliseconds. So almost 4 times faster just by that small modification there, by handling the bit shifts ourselves. So this just goes to show that it's always worth benchmarking. You can't assume anything. You can't assume that you're going to do better than the compiler, and you can't assume that the compiler is not going to shit the bed, because apparently sometimes the compiler will shit the bed. And of course, these results are only hold for the Microsoft Visual Studio. If you tried to compile the same stuff in GCC, it might actually be faster using unions, or even the Intel compiler. The Intel compiler is generally the fastest for compiling for x86, so I would imagine it would be able to optimize this code a lot better. But for good old Visual Studio, yeah, it shits the bed for this code representation. So we learned something new, and that is don't use the union access or the constructor to pack and unpack inside of a loop. Anyways, it's a convenient way to access these members outside of any critical code path. But in a critical code path, you don't want to be using this kind of representation. So yeah, there is our fade in standard code, and we get 1.29 milliseconds. Now comes the fun part. We're going to try to do this in SSE. And it's the same basic principle, which is to say, that we want to unpack our components. This is the unpacking part here. And then we want to multiply by alpha, and then we want to shift right by 8. And then we want to repack our components together and store them. So how is this going to work out in SSE? Well, let's take a look. So we'll go to our good old friend, where is it? Fade SSE. Here it is. And yeah, I'm just going to have to explain this now. Shit. This is where I have to do stuff. So the first parts, I hope, are fairly self-explanatory by this point. We want to set one register with alpha values, and they're going to be 16-bit alpha values. We'll get to that reason a little later. And another register, we're going to set it with 0, because we need a 0 register. Then in the body of the loop, we're going to load our source pixels, which we haven't done yet, but it's quite similar to store, except with store you supply the pointer to the address, and you supply the register to be stored. With load, you just supply a pointer, and then the return value goes into the register that you want to load the data into. So we're loading into the source pixels register. And then we have to unpack the values. So first of all, why are we unpacking? And second of all, how are we unpacking? These are the two questions that I have to answer, and that I will answer if I can get my whiteboard up. And then I want to delete this part of the whiteboard and get another thing here. Okay. So the operations that we have to perform are multiply by alpha, and then shift right by 8, or divide by 256, I should say. So we know this is high, this is low. This is going to be called SRC, the source pixels. And the contents are ARGB, 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 ARGB. So here's the contents of our source after we've loaded it. Now, ideally, what we would like to do is, these A's are not important. They're from the back buffer, and they don't mean shit. The alpha that's important is the one that got passed into the function. And so what we would like to do, for example, is we would like to, move the alphas into here. That one doesn't matter, but line them up with the RGB. And then we would like to multiply them down. So we want to use a multiplication operation to give us results here, 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 and here that we can then shift and then store back into the memory. But there are multiple problems with this. The biggest problem is that it's not possible, because the results would not fit into another register. Think about it. Multiplying a 8-bit value times an 8-bit value. How big is the result going to be? It's going to be 16 bits in general. If you've got a general 8-bit, that can be anything from 0 to 255, multiplied by another general 8-bit, you're going to get generally 16 bits of result, ranging from 0 to... who the fuck cares? It doesn't matter. What's important is that you're not going to be able to fit the results into a destination register. So multiplying 8-bit by 8-bit isn't going to work. Second problem is of course, that instruction doesn't exist, multiplying an 8-bit by another 8-bit value to get an 8-bit result. That instruction does not exist because it's not possible. So forget about that. We have to get 16-bit results. Now the problem with that is there is no instruction. I mean, there are weird instructions. You can multiply 8 bits by 8 bits. They're not going to work for us. Forget about them. In general, you cannot multiply an 8-bit value by an 8-bit value to get a 16-bit result in your register. How would that work? You wouldn't have enough. You'd have to fit the results into 2 different registers. So what we need to do is we need to expand these 8-bit values so that they are 16 bits wide. So instead of, each register holding a value like OXFF or OXAO, this would be expanded to OX00FF or whatever. Doesn't matter. That's the first thing you're going to want to do. Expand your 8-bit channels to 16 bits so that you can then multiply them together. All right. Where's my code? Here it is. So that's what this is doing here, this unpack low and unpack high, extended packed integer 8. This is the unpack part of the story. Now, what do these instructions do? Well, I'm going to first introduce you guys to these 2 web pages. Very useful. Well, one more useful than the other. You can find them. Mainly, I've come to these the Microsoft web pages just by searching Google for the actual name of the intrinsic. And it'll give you a short description, the form, the actual instruction that the intrinsic translates to, and then an algorithm that shows you what the intrinsic is doing. So fairly useful, and I use this mostly when I was learning. Recently, I've come across this web page. It's much better. This one gives you an algorithm and a description. It also tells you what version of, what CPU ID version you need to be able to run the instruction. And it tells you what include file you need, and so forth. And quite important for later on when you're really getting into the fine tuning, it tells you the latency and the throughput of the instruction. This is important, but not right now. I'll come back to this topic later on, but it's not important for right now. So the Intel webpage gives you a way better way to search for instructions and gives you better description. But you might need to use them both. One thing I would caution you about is that sometimes the names of the intrinsics are different between the Microsoft and the Intel. Mostly they're almost all the same, but I believe a few of them are a little bit different, so you have to be wary about that. But in general, I would recommend using this web page to search for whatever. You can search by name of intrinsic, you can search by name of instruction, or you could maybe search by other things that I'm not sure about. You could also filter by whatever technology you're interested in, and by categories of instructions. Okay, so what does packed... oh wait, this is multiply. I actually want unpack low epi. Well, it doesn't matter. Well, it interleaves the lower 8 signed or unsigned 8-bit integers in A with the lower 8 signed or unsigned 8-bit integers in B. So we're interleaving integers, which is interesting. But you might think, first of all, well, how does that work? How does that unpack things? What's the correlation between interleaving and unpacking? And you might also look at this and be like, I don't really understand what's going on here. So that's why I Googled this, because it's going to be way better than any diagram that I draw. So this is what the instruction that this intrinsic translates to is this instruction here. And this is what it does. So it takes unpack low EPI8. So the EPI8 part means we're going to be working with 8-bit packed integers. Now the low part means we're going to be working with the low 64 bits of each of these registers. So we take A and we take B and we interleave them like this. So the first byte of A goes into the first byte of the destination. And then the first byte of B goes into the second byte of the destination. And then the second byte of A goes into the third byte of the destination, and so on and so forth, interleaves them. The reason why we have low and high is because if you're interleaving, you can only fit half of A and half of B into the destination because you're going from 2 registers into 1. So that's why you have a high version and a low version. And yeah, so this will interleave. Now, if you set B to 0, what you're going to get is you're going to get the bytes of A going into the low part of every 16-bit integer, and the bytes of B being zeros, just filling the high half of every 16-bit integer with 0. So this will, if you set M2 in this case, or B, if you set it to 0, all this is going to do is unpack the bytes in M1 so that they become 16-bit integers in the destination. So if you want to unpack, you need to have zeros to unpack with. It becomes a little more complicated when you're working with signed integers. If you have signed bytes in here, then depending on whether the number is negative or positive, you're going to have all zeros or all ones in here. But that's complicated, and we won't be covering that because it's not very useful for us. But just know that this unpacked instruction, although it is mostly used for unpacking, because you're interleaving stuff, it could also be used for other things. But mostly we'll just use it for unpacking. And that's how it works. So, getting back to our code, we're going to unpack the low half of our pixels into register named source low 16, and unpack the high half into source high 16. So this is the low end. So this would be 3G3 R3. And after, where's the center line? So here's the center line right here. Between the high 64 bits, and the low 64 bits. And if we, let's see which one of these is this one. So now if we go, so unpack low will give us what? It's going to give us, right, B0, and the top half is going to be all zeros. R0, G0, R0, R3. There we go. So there's I fucked it up. Whatever. You know what? I don't care. Unpack high. I should have switched to a different layer for this one, but I probably won't hurt me too much in the long run. So here's what we get after we unpack. We got these 2 registers here, which hold the 16-bit values of these channels. Now, we're going to multiply them by alpha. Now, alpha has already been prepared for us because we did set 1 with our alpha into this register here. So we have a register and all the 16-bit values are filled with alpha, which is, at a value between 0 and 255. So the top 8 bits of each of these packed 16-bit values they're all set to 0. All right. So the next step is to multiply these registers by alpha. So we're going to multiply 2 packed 16-bit values together. Now, here's the problem. We can multiply. There are instructions for multiplying packed 16-bit values together. We have this. It is possible. However, the thing about multiplying two 16-bit values together in general is if you multiply OXFFFF by OXFFFF multiplication, your result is going to be, correct me if I'm wrong, but I believe it's going to be it's going to be FFFFFFE. This will be your result. That was dyslexia there, wasn't it? There we go. So the results, again, the same problem we had with bytes, they aren't going to fit into the destination registers. This is a problem. However, in our case, well, first of all, the way this is handled by SSE is that there are two instructions for multiplying 16-bit values together. Now, there might be more, but there's two that we are going to be aware of for the time being. And I have created a diagram for this because I am prepared. But in order to show the diagram, I'm going to have to hide a bunch of other shit. So we'll hide this, hide that. And then we're going to show this diagram. So in general, when you want to multiply two 16-bit integers together, your result is going to be 32 bits. There are two instructions, mul low and mul high. Now mul low, mul high, they do the same operation. They multiply these two together. But mul low puts the low 16 bits into the destination, the position in the destination that corresponds to the positions or the position of the two sources. So multiply the first packed integer in A and the first packed integer in B, and the result goes into the first packed integer in C. Which part of the result goes in depends on which instruction you're using. You use mul low, you get the low 16 bits in here. If you use mul high, you get the high 16 bits. Now, because we're multiplying values where the top 8 bits are 0, our result is actually going to end up being, well, let's just see. Let's say our color and our alpha are both FF. So OXFF, wait, let me, OX00FF times OX00FF. So our result is going to be EFFF0000. So the top is going to be zeros anyways. Who the fuck gives a shit? So we use mul low for the case where the top 8 bits are all 0, and then we get the exact result. There's no truncation or anything. So yeah, we can use the mul low in order to multiply two effectively 8-bit values to get a 16-bit value, as long as you extend your 8-bit values before you perform the multiplication. And that's what we do. So let's go back to, that's good, that's good, that's okay. Well, I feel like we're missing something. Yeah, that's what we're missing. And also, that's not it. That's not it. Ah, that's it. I think that's all we need. All right. So, multiply these ones together and take the low 16 bits of the result. So we'll use mul low, which is what we get here. Mul low 16 and mul low 16 for the unpacked low part and the unpacked high part. We're multiplying them by alpha. And I don't think we need diagram for the rest of this because it's really simple. Once we have that 16-bit value. Then we shift right by 8 bits on both sides. Let's draw it. Let's be R1, 1, 1, and 0, 0, 0. Here we go. So here's our 16-bit results of the multiplication. So the next thing that we want to do is shift right by 8 bits. By 8 bits. And what that'll do is that'll just take these high 8 bits, shift them over. It's the same as dividing by 256. And the result is going to be, and then RGB. And the same will be for here, so I'm not even going to write it. But you get the general idea. So we go, let's see here. Right. So now we shift by right. We shift right by 8 for both of these. And finally, we have to combine the high and the low together, repack them into 8-bit values. Because obviously the graphics card is not going to understand 16-bit values for the back buffer, for the pixels. It needs them packed back into 8 bits. So we use the packus, which is pack unsigned with saturation. And that will pack our values back into 8-bit values. G1, B1, R0, G0, B0. And what pack does is very simple. What it actually does is, where is it? Let's go packus. Now we have to find the green one. Here it is. So convert packed 16-bit integers from A and B to packed 8-bit integers using unsigned saturation. Now, saturation means, well, unsigned obviously means we're treating them as unsigned values from 0 to 65, 5, 35 or something. I don't know, whatever. And saturation means that, let's say the value here in these 16-bit, if it's greater than, so if value is greater than 255, then the result is going to be 255. So it doesn't like wrap over. It doesn't just ignore the top 8 bits and store the bottom 8 bits. It if the value is greater than what can fit in a byte, it's just set to the maximum that can fit in a byte. That's what saturation is. And if you had signed, then it would also go in the opposite direction. If it was less than the maximum or the minimum that could fit in a byte, it's set to the minimum. But since we divided all of our values by 8, there's no way that they're going to be greater than 255. So the saturation doesn't come into play. All it means is that we take the low 8 bits of each of these 16-bit packed integers and fill them into here. So this would become B0, G0, 2, 2, 1, 1, 1. There. And that's the final result of all of our calculations. And then this is just stored back into memory where we loaded the original source pixels from. So you can just like normal functions, you can nest intrinsic in functions within each other. And I see a lot of people writing code like that, but it is more difficult to read in most cases. I do it here mostly just to show that it's possible, but I often prefer just setting them, giving each intrinsic operation its own line. And you'll see that actually looks nice when you look at the decompilation or the disassembly. But yeah, you can, they work a lot like normal functions. The only difference between an intrinsic function and a normal function is normal functions are in libraries. They're not part of the compiler itself. An intrinsic function is built into the compiler executable. Just like the operation of incrementing a pointer or incrementing or adding two integers together. You don't need to link to a specific library in order to do that. The compiler just knows what kind of code to generate for that operation. And the same way, the compiler just knows what kind of code to generate for an intrinsic function call. That's really the main difference between intrinsics and normal functions. But anyways, I'm getting off track here. So that's the whole shebang right there. You load your source, you unpack it into two different registers holding the 16-bit, the bottom 2 pixels and the top 2 pixels. Then you multiply them by alpha, divide by 256 by shifting right by 8, and then you pack them all together into a single register, and you store that back in memory. So let's see what performance we can get. Our optimized version of the C code gave us 1.290 milliseconds. Let's go fade SSE build. Start, and we get, just as before, we get the same result. Same effect, so there's nothing wrong with our code logic. And yes, log file was updated. Let's see what we got. So here we get about 250 microseconds. So a little bit of quick math will show us that this is about 5 times faster than what we get with our standard code. That's a 500% increase in speed. That's pretty good. And it's about what you would expect when you think about it. Because with a single operation, looking at some of our other things that we've got here. Jesus Christ. Yeah. So with a single operation, we're basically processing 6 channels at a time. So we would expect, about 6 times increase, but you never get like your full. There's always, diminishing returns and all that bullshit. So a 5-fold increase is about what you would expect. And that's what you get. Oh. All right. So let's just take a look at the disassembly of this. Decal spec, no inline. And we're going to see just what it looks like. Shouldn't be too much in the way of surprises. So we'll go to the disassembly. So here we're setting up our loop variables. We're setting up our registers that we're holding our constants, alpha and 0, in here. And here's the body of the loop. And as you notice, the intrinsics, they basically they boil down to more or less one instruction per intrinsic. So here's our load, and it translates into a move. Here's our unpack low, unpack high, unpack high. So you see that these two, unpack low and unpack high, translate into 3 instructions, 2 unpack instructions, and a single move to just fix things up. Because like I said before, our intrinsics can take 2 sources and 1 destination, but the actual instructions one of the sources is also the destination. So that means that the compiler has to sometimes insert some extra moves just to make it all work. And that's one of the beauties of using intrinsics. You don't have to worry about that bullshit. So yeah, more or less say one instruction per intrinsic thing here. Multiplication, again, mul low translates into p mul w. Shift right translates into p shift right, or shift right logical word. And pack translates into pack. And then store translates into move DQA. And then here you have your loop variable, increment the pointer, compare it with the end, and then jump if they're not equal. Or jump, I don't know what JB means. Jump if, I don't know what JB stands for. Whatever. Jump if we are still less than that. At any rate, there you go. Very simple. Very straightforward. And a huge performance increase by using SSE. All right. So another thing to be mindful in optimization is taking advantage of special cases. Oftentimes, special cases, you can cut corners and execute them faster than you would for the general case. So the general case of fading by some kind of alpha value, you can have special cases where you're just fading by, for example, half. If you just want to reduce the color, I guess, the brightness by half, basically by using the alpha value of 128 or 127, somewhere around there. That's a special case, and that can be optimized. Let's say alpha, we're going to fade by half. So alpha is going to be 128. Now, if we revert our equation back to its proper form, which was, or no, not its proper form, but the form we have, 256, divided by 256. 128 divided by 256, multiplying by 128 and then dividing by 256 is identical to multiplying by 2, which is identical to shifting right by 1. So instead of doing the whole circus where you multiply by alpha and then you divide by 256, you can just directly divide by 2 and save yourself a whole lot of hassle. You can save yourself a multiply, right? Multiplication is a non-trivial operation, not as slow as division, but it's still slow. Oh yeah, I wanted to do a thing, and I'm going to do it right now because I just remembered it. Fade. Fuck you. Fade shift. So our good old friend fade shift. I'm going to go to definition. And let's try dividing by 255 just to see how much slower it is. So this is the optimized version that doesn't use the union access, uses just shifting. The version that divides by 256 via shifting gave us about 1.29 milliseconds of performance. So let's see what the version dividing by 255 gives us. 255 is a more accurate result. So if there is no difference, we would prefer to divide by 255. But as we can see from these results, it is almost twice as slow. Not quite, but almost twice as slow to divide rather than to shift. So if we change this to just by 1, just fudge the numbers just a smidge, we can see that performance is much better. I just wanted to show that off there just to make sure that you can see that there is an actual tangible benefit. So by doctoring our results and giving us about 0.4% error, we can increase performance by almost 200%. Which in my books is totally worth it. All right, so getting back on track here, we want to do fading, but only by half, so that we don't have to do the multiplication. We can just divide by 2. So here's what that looks like in SSE. You see, it looks very similar to what we had before, except here we have multiplication. Here we have no multiplication. Instead of shifting by 8 bits, we're only shifting by 1 bit now. So let's see what this performs like. Now, if you recall, the normal version did it in about 250 microseconds. So let's see how fast we can do it here. See, I can't adjust the alpha. I'm hitting the scroll wheel. It's not changing because it's fixed to half, or 128. Now we can go to, where is it? Log file. So we're down to 192 microseconds, which is better than 20% increase in speed. So that's not bad, right? That's pretty good. But we can do better. Now you might be saying, hey Chili, why are you even bothering to unpack this bullshit if, I mean, the whole reason for unpacking was we wanted to multiply the values together. We could only multiply in 16 bits, but we're not multiplying. We're doing shifting. So there isn't any reason why you shouldn't be able to shift by 8-bit boundaries, shift packed 8-bit numbers, except for one reason, and that is that instruction does not exist. I've got selected here all the SSE versions, and I typed in shift right logical. And here you go. This is all you get. And as you can see, there's no 8-bit version of the instruction. If I go shift right algebraic, nope, only 16 and 32. And logical shift, only 16, 32, 64. And there's 128, but this one's special. We'll talk about it some other day. It doesn't shift by bits. It shifts by 8 bits at a time, so it doesn't work for us. But anyways, the deal is we can't shift packed bytes. It doesn't work. Here's what would happen if we tried it. I mean, we only have the smallest shift we have is shift 16. Imagine you have 2 packed bytes side by side. The values are 3 and 3, and you shift right. What are you going to get? You're going to get a 1 in here, which is correct. 3 divided by 2 is 1 when you round down. But for the second, for the lower byte here, what's going to happen is the low bit is going to get shifted into the lower byte because we're shifting on 16-bit boundaries. So there's no barrier between here and here, and the byte or the bit shifts over, and the result here is not 1 but 129, which is completely wrong. Now the good news is, if we're clever, we can get around this. What we can do is, with a small little fix-up, we can shift packed bytes. Because the problem is this one bit that leaks in from the neighboring byte. We don't want this bit to leak. So what we can do is, if we're shifting an 8-bit number to the right by 1, we know that the result is going to be, well, let's call it x fuck. All right. So let's say we don't know what the bits are, but we're shifting an 8-bit number to the right by 1. We know that the very left bit is going to be 0, and the rest are going to be we don't know. So we always know that this bit has to be clear if we're shifting right. So what we can do is we can create a mask that keeps all the bits except for the top bit of every byte, because we know that this one always has to be 0. So we can just clear this one out by using an AND mask. Logical AND with this mask will mask out the top bit. And so in case the bit leaks from the neighboring byte, it'll get masked out and we'll just get the proper result. So this mask will be It's going to be OX, and it's going to be F7, so 7F. So if we fill an XMM register with 7F, 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 we can and mask, and then we can simulate 8-bit shifting. And because we use this mask, it doesn't matter which shift instruction we use. We could use a 64-bit shift, 32-bit, or 16. Doesn't matter. So that's what we do here. We do the packed shift. So I create a shift mask up here, and I just do that by set1 packed integer 8 bits. So I fill a register with the byte 7F repeated, and then I load. I shift right on 16-bit boundaries. Then I AND with our shift mask, and then I store. So this is a lot shorter than this. So let's see what kind of results we get. This one was 195-ish, maybe 195 microseconds. Let's see what our packed version does. I mean, they're both packed, but this one is packed more. This one's packed with 8 bits. So fade half packed SSE. Let's see what we get. Start. We still get the same value. We shouldn't get any difference in here. And if we look at the results, now we're at 150 microseconds. So that's 100 microseconds faster than the general case in SSE. Not quite double performance, but getting close. Maybe a 40% increase or 40% lower execution time. Execution time? Yeah, I said that weird. What do you got? You got a problem with that? All right, so there's our good version of that. Now, let's just look back for a second at our unoptimized version, because we've been neglecting it, and it feels a little lonely. So fade half. Well, if we do it the old-fashioned way with the union, we know it's not going to be pretty, but let's just take a look. So fade half. Build that. All right. And take a look at the values. And yeah, so it's like, it's faster than the other one. The other one was like, I think about 5 microseconds. This one's 4.26, or 5 milliseconds. This one's 4.26 milliseconds. So it is faster. It's not that much faster, and it's still goddamn slow, because the compiler is, as I so often like to say, shitting the bed here. So this sucks. Don't do this. Now, what if we were to do the same thing we did in SSE? Because think about it. We can use any shift we want as long as we use a mask afterwards. So we can even shift the packed values without SSE. As long as we use the mask, we'll still get the same result. So here I take the value at the pointer address, I shift it right by 1, and then I AND that with the shift mask and store it back where it came from. And if I build this, let's see, fade half packed. So let's see how this does. This one doesn't do the shitting the bed thing by using the union or the constructor to unpack and pack, because it doesn't pack or unpack at all, right? Fade half packed. And it does this kind of, this is like this is single instruction multiple data without SSE instructions, just with normal standards x86 instructions. But as you can see, the results are pretty good. They're not bad. They're like 3 times faster than the standard general case. And they're starting to get close to the SSE's general case. They're still worse than the SSE's slowest version, but that's a respectable speed. And nothing to thumb your nose at. Now, let's see what else I want to talk about here. All right. So what we might want to do is compare this fade half packed to fade half shift, because we have the fade half version here where we use the union to unpack and unpack. But what if we didn't use the union? How would that compare to the this version here? And this is where things get interesting. So let's try fade half shift. Now we can't expect to do better than the packed version because it's just a simple shift and mask. Fade half shift. But we'll expect to do quite a bit better than the shit the bed version. So we're gonna start. Let's just take a look. So our packed version did 379 microseconds. This version does 380 microseconds, the exact same speed, which is not to be expected. Now let me show you something else that's freaky. It'll blow your mind. Maybe not. I'm gonna go fade half packed, fade half shift. I'm gonna call them both. And then I'm going to put a breakpoint here and here. Now I'm going to start. Now it should do the thing that I'm hoping it would do. Alright, no. Alright, so it stopped on this breakpoint here for fade half packed. Continue. Stopped here again. Strange. Continue. Stopped here again. Why is it only stopping here? It's never stopping here. Let's remove that breakpoint, go again. And now it's not stopping at all. Stop the program. Sure. And the breakpoints are gone. So what the hell? I set a breakpoint here and here, but it only ever triggered this one, even though I'm calling both these functions. Now the answer to the question is that the compiler will actually generate identical code for these two routines here, these two functions. So the compiler is smart enough to see us unpacking these values, shifting right by, just basically unpacking them and then shifting them right by an extra 1 bit, and then repacking them. And it's saying, actually, what you actually want to do with all this is you just want to do this. So I'm just going to do this. So it is super smart when it comes to figuring out this bit shifting bullshit, but it is super dumb when it comes to figuring out this bullshit. So go figure. It's just a weird thing with the friggin' compiler. And I thought it was interesting, so I showed you. Actually, what I'm going to do, just to to basically beat this dead dog. That's not the expression. I forget the expression. Beat a dead horse or something? I don't know. Anyways, so we're going to set a breakpoint here. Oh wait, no, because I got both of these here. So we're just gonna do that. So we're gonna set a breakpoint here, and yeah, we look at the code. Sure. And we see it's basically here. We're shifting right by 1. We're ANDing with our mask, storing, and then loop. Load, shift, mask, store. So exactly what we wrote is what's being done here. And stop. Now we're going to do it the other way. We're going to comment this one out. Uncomment this. We're going to go to game. We're going to uncomment this. Comment this. Build. Start debugger. Yeah, sure. Go to disassembly. And here you see it's doing the exact same thing. It's loading, shifting, masking, storing. Even though the code is completely different. The end result is the same, and the compiler can see that, and it can make your code much faster. I mean, if it were to do this the dumb way, it would load, and then it would shift and mask into this variable here, shift and mask, and then shift back, or together and store. But it can reduce that to the very simple shift and mask once. So sometimes the compiler is smart and sometimes it is dumb as rocks. That's all I wanted to show here. Now, I'm going to show you one more thing. We can actually make the SSE version a little faster even. And the way we do that is with a little instruction called average EPU8. So what average does is it takes the average of the values in the registers and so adds them together, divides by 2. So what we can do is if we load one of the registers with 0, we're adding source plus 0 divided by 2, which is just source divided by 2. It allows us to divide 8-bit values by 2 without, doing this shift and mask bullshit. So now we can do it in one instruction instead of 2 instructions. Even faster. So what we do is we go fade half, average SSE. Build that motherfucker. Remember, we had 150 microseconds for the last one, I think. Let's see what we got now. We're going to load our log file. 143, 44, 139. So best we can do is 140, I guess, around. So a little bit faster. You can't really improve much because when you remember, just the operation of just repeat storing was like 125 microseconds. So you're not going to be able to do much better than that, especially when you have to load and store in this one. But there you have it. Very nice stuff. And I think that is all we're going to do in this episode. Next episode, we're gonna keep moving on with other slightly more complicated operations as I introduce more and more stuff about SSE. But until then, adios. Hello, I'm Chili, and this is my wife. This is part 3 of the SSE hand relief. Very nice. That is probably the worst Borat impression you will ever hear. So at least you've got that out of your way now. You can cross that off the bucket list. Okay. So first thing is first. Before we get started, what we need to do is we need to go to Team Explorer. You want to synchronize with the old repo, and then you want to make a new branch, and you want to create a new branch off of origin tint your taint, which I'm personally very proud of that name. Next, what you're going to want to do is you're going to want to listen to the smooth stylings of Chili as he regales you with SSE nuggets of golden wisdom. I made diagrams. And by made diagrams, I mean I stole them off the internet, which is actually way better for you, because I suck at drawing diagrams. And drawing in general. It's just not my forte. So what are we going to be doing today? Well, the title of this is the SIMD Shuffle. We're going to be doing a little bit of the tint and shuffle, as I call it. It's not quite like the slap and tickle, but it's kind of close. So the two operations we're going to be working with is tint, which is basically to tint an image with a color. And the other one is blend, if I can get it in here. Blend, and that's just blending two images together based on some alpha value, weighting between the two images. So for tinting, these are both basically operations of alpha blending, right? Now let me take a look at. So you've got your basic alpha blending formula here for integers. You multiply one color by your alpha value. You multiply your other color by the complement of your alpha value, or 255 minus alpha if you're working with byte values, which we are. And you divide by 256. Why? Because it's way cheaper than dividing by 255. Now, in the situation of fading, color 2 was black, which is 0. And that's not discrimination, it's just a fact. And so what you get is you get this term cancels out, and you end up basically just multiplying by alpha and then dividing by 256. Now with the tint, you can't do that. That simplification is not available to us. With alpha, we've got one value which changes per pixel. That's per pixel. And then we've got another value which is a constant. And we can still make a little bit of, I guess we can make some use of the fact that this is a constant to provide some optimization, but we can't just cancel the whole damn thing out like we did with fade. So how do we handle tinting? All right, so tint, here's the basic idea. We're iterating through all the pixels in the buffer. And what we're doing is, we're doing the same thing as the formula, right? We're multiplying by alpha here. C is the color that we're tinting. D is the destination color. That's the pixel on the image that we're tinting. And we multiply color by alpha. We multiply the pixel that we're actually tinting by the complement of alpha. We divide by 256. We do that for all three channels. We pack them together and we put that onto the image. Now this works, and as we've shown before, using the unions like this, very slow, not very good. So the better thing to do is to shift and mask. And by shifting and masking, we can avoid the compiler shitting the bed. And we get a faster result. Now pre-computing is even faster. We can note that this value of the color, the tint color times the tint alpha, is going to be the same for every single pixel in the image. So we pull that out and we pre-compute that outside of the loop. And then we blend as usual. And that is even faster, I think. Let me check. Tint shift and tint pre-computed. So let's take a look at, and gain all together for you. Nice. So, very nice. Oh, I told you that was the last time you're going to hear that, and I lied. All right, so there you go. You got your red tinting goodness. Let's look at the log file. So that's 2.6 milliseconds. And if we go tint pre-computed, we'll run that. Yeah, we can change the alpha. We control the horizontal. We control the vertical. Yeah, that's faster. That's quite a bit faster. So the compiler is not smart enough to pull that that operation out of the loop. We have to do that ourselves. And indeed, that is what we did with tint pre-computed. And tint pre-computed packed, all that does is here we have the pre-computed channels and we add them channel-wise and then pack the results. Here we pre-pack the pre-computed channels and we add them in afterwards because we realize that by alpha blending the scaled source and destination colors, they won't overflow. They won't add up to, the channel values won't add up to more than 255 if we've done it correctly, right? Because we're multiplying by 255 and 1 minus 255, and we're also dividing by 256. So overall, they shouldn't overflow, so we can just add them directly here. Again, we've done this before, and this is all known. Tint half packed is, again, we do the packed thing, except now we also divide by 2 by shifting the whole packed value, and in order to prevent the ones from leaking into adjacent channels, we mask with this mask here. And again, that works very nicely. Okay, so that's all the tint bullshit that you have to know. Let's get on to the fun stuff, which is how do we do that in SSE? So we gotta scroll all the way down till we get down to the SSE. So tint SSE. Here's where the magic happens. Now I'm not gonna go over this because you already know what this loop is doing. We're looping by pointer here. And here we're just setting up some constants, 1, 0, and this is 255, right? In 16-bit values. And this constant is the color. And we're setting the color in all 4 of the packed 32-bit values. And so what we do is we load the destination pixels. Then we unpack them. I've talked about unpacking before, I think. Yeah, I did that. And we're also going to unpack color. And we want to broadcast the alpha values so that they match up with the with the color components in the destination pixel. So what we want to do is we want to multiply our color components by alpha values. We want to multiply it down like this. The problem is that our alpha value is stuck in the top of this 4-channel color. So what we want to do is we want to broadcast this alpha into all the channel positions here like this, and then we can multiply our color by the alpha. Now, I mean, it depends on what we're multiplying. If it's the pixel that we're multiplying, then we want to multiply it by 255 minus alpha. But the same idea holds that we want to get the alpha value from this position into these positions. And the thing that we use to do that is called a shuffle instruction. This allows us to rearrange the values in the vector register. So shuffle low, shuffle high. What do we do? How do we do? The way you do it is you do it half and half, the top and the low part. So let's look at the low part first. This would be shuffle low. Basically what you have here is you have 4 multiplexers, and they can select any one of these 4 values, and each one of them can select that value and put it in its corresponding destination position in the register. Now the way you select this is the 4 values you can choose. So that means that you use a 2-bit value to select. So obviously 0, 0 is going to be this one. This would be 0, 0. This would be 0, 1, 1, 0, and 1, 1. And using this situation, you can rearrange these 4 sources into the destinations. Now, the beauty of shuffling is you don't have to, the idea, when you think about shuffling a deck of cards, you think of rearranging the order, but you don't have to maintain the same elements just in a different order. You can copy, so you can use, for example, 0, 0, 0, 0, 0, 0, 0, 0, and that will copy the value A into all 4 of these positions. So shuffle is not only a shuffle instruction, it's also a broadcasting instruction. And shuffle low will allow us to rearrange the low 4 elements, and shuffle high will allow us to rearrange the 4 high elements. Now you might ask yourself, why don't you just make a single instruction that allows you to rearrange them all at once? And that would be nice, but there's a problem. And the problem is that when you use shuffle, you have to specify an immediate value that the instruction bakes inside of itself to determine how the rearrangement is going to be happening. And that value can only be 8 bits. The immediate value for SSE instructions, maximum 8 bits, as far as I know. And if you, a little quick math, you need 2 bits for each one. You're using up all 8 bits right here. So that's why you have shuffle high, shuffle low. For the 32-bit shuffle, there is just shuffle. There is no high or low because 32 bits, there's only 4 32-bit values in an SSE register. So you don't need high and low. You can do it all with one instruction. But with the 16-bit shuffles, you need high and low. And because of that, you can't cross from here to here. You can't shuffle a value from here to here. It doesn't work. So you'd have to do, if you want to shuffle across the lane, as they say, cross lane operation, you have got to do more annoying bullshit. Like, for example, shuffling with the 32-bit shuffle to cross, and then shuffling with 16-bit to get it to where you want in the 16-bit. It's kind of annoying, but that is how we do. So with this one, what we're doing is alpha is equal to shuffle low, color 16. So we're broadcasting the top element in the low part of color 16 to all 4 areas. We're broadcasting the alpha to all 4 components in the low half of alpha, with the source being the color that we are tinting with, right? So we're broadcasting the alpha from the tint color in the low parts. Then we're going to do the same in the high parts. Now we subtract the alpha from the 255 values, the ones, as I say. I call it ones because in binary it's all ones, right? We subtract alpha from that to get the complement. And now we have the complement. We can multiply the complement by our pixel to get the multiplication. We can multiply the alpha by our original color. Then we can add them together, high and low. Note that in color, high and low are the same, right? There's only one color, so we don't have to do high and low. We just do color. And then what do? Then we shift to divide by 256, and then we pack and store. Simple, not too difficult, I hope. This macro here, this is a macro, and it generates those values. Let me just see, it doesn't tell me the result. It generates the 8-bit value immediate that the shuffle instruction needs. So this one would generate 255, I believe, because it's just 1 1 1 1 1 1 1 1, right? But it's easier than writing it out, in like hexadecimal. It's more readable. I believe Visual Studio 2015 supports now binary literals, but I don't have that yet. So, anyways, just use shuffle. It's a good macro. All right. So that's tint SSE. Now the problem with that is, of course, in here we are multiplying, again, we're multiplying the alpha by the color. And or we are shuffling the alpha out, or multiplying it by the color every single pixel, but that never changes. So what we can do is we can do that bullshit up here, and then all we've got to do is just add, where is it? Yeah, we just add the result of all this bullshit. So we pre-broadcast the alpha, we pre-multiply, we pre-divide, and we pre-pack it. And then all we have to do is just add the packed values. Because like I said before, we're not going to get any overflow because everything's been scaled already. So there should never be any overflow. So this is basically analogous to, our packed version, which is standard code, x86 code. And this one, so here we have tint SSE, and here we have tint pre-computed. So let's check the performance. Tint SSE. Take a look at that. Works. And the performance is, no, that's not it. So, 260 milliseconds. Okay. I mean, it's obviously better than what we were doing before without SSE. Let's try tint SSE pre-computed. That's not the name of the, that's not the name of the function. Let's go back. Come on. Where is your print okay, whatever. Fuck. Yeah, I got you. I got the names backwards though. Pre-computed SSE. There we go. Build. Run. And again, works like a charm. Yes. So before we were at 260, now we are at 250. So barely any change. And you might be asking yourself, well, surely that doesn't make any sense. It does if you look at the disassembly. I'm not going to do it here, but if memory serves me correctly, basically the compiler was smart enough to pull this bullshit out from here, and when it compiled this to machine code, which it could not do, strangely enough, in just the standard C code, but it was able to do it when we built with intrinsics. Just weird stuff. You can't really predict when the compiler is gonna, go all MVP on you and when it's gonna shit the bed. As always, you gotta benchmark where it's important. Can't take anything for granted. All right, now the next thing we can try is tint half SSE using the averaging function, and that's if we are ensured a 50-50 value of tinting with the color. Then all we need to do is call average EPU8, and that's super fast. This is better than before when we were calling average EPU8. We were just calling it with the 0. We were using it as a bastardized divide by 2 in 8 bits. Now we're actually utilizing its potential a little better. We're actually doing an average. That's all. If you do an alpha blend between two values with an alpha value of 127 or 128, you're basically just taking the average of the channels in the two values, the two images. So tint average half it's going to be fast. You can check it yourself. It's not important. What is important is that now we are going to move on to the second function I wanted to cover in this episode, which is blending. Now, blending it's like tinting. It's like fading in that it's an alpha blending function. But now we're taking the values of two images, the pixels, and we're blending them together. So now we don't have a constant color that we can pre-compute once for the whole operation. We have got to compute per pixel. Images changing per pixel. The only thing that doesn't change per pixel is the alpha value, because blending is just an operation, blending based on some alpha, some weighting between the two images. How much do we want of image A? How much do we want of image B? So the alpha value doesn't change. So we can pre-calculate the alpha. We can use set 1 here. So, and I'm not like up here, just for demonstration's sake, I did the shuffling. But we don't have to do the shuffling. We can just use set 1. Now, in general, and I wanted to talk about this. In general, inside of the loop where you're doing your actual processing, you should not have any set 1 or set functions, because these are slow. They're very easy to understand, easy to write, but they're slow because what they do is they load a value into your register, into your standard x86 registers. Then they transfer it from those registers into the SSE registers, and then they shuffle. And that is slow. You don't want to be doing that for every single iteration. You want to be loading with SSE loads like, mm load and mm store. You don't want to be using set. But it's fine outside of the loop, obviously, because you're only doing it like once. For all these operations, it's like over 1 million operations, right? So it's fine in here. It's not fine in here. That's all I wanted to say. So we set up the alpha, we set up the complement, we set 0. One exception is you can use set 0 inside of a loop. It's fine, because set 0 just boils down to a single exclusive OR operation. If you exclusive OR any value with itself, the answer is always 0. So this just boils down to exclusive OR. It's super fast. So I use this all the time. But you never want to be using these set values inside of the functions. I've benchmarked it myself, and it is considerably slower. All right. So that out of the way, let's talk about Blendy. So what we're going to do is we're going to load the source pixels. We're going to load the destination pixels. That we're blending from and we're blending to. We're going to unpack all those pixels to 16-bit values. Then we're going to multiply them by the alpha and the complement of the alpha. And then we're going to divide them. Then we're going to add them. And then we're going to repack them and store them. So that's it. It's very simple operation. But it's, it takes more work than tinting. So we go blend SSE and shit. Okay, so I need another. I didn't do this here. I want another image. So I got Borat here. So we're going to add Borat to the. All right. So we're going to start with the bees, not the bees, and then we're going to blend on top of that Borat with the alpha value that we control with our mouse wheel. So here we go. Here it is. We can have the bees, not the bees, or we can have Borat. So that works very nice. Very nice. And we go to log file, and we see that this is a more expensive operation, obviously. It's taking on average, about from 500 to 600 milliseconds to blend two full screen 720p images. So the question is, can we improve this any? The answer is yes, we can. Yes. Where's the code? Here it is. All right. So the first thing that actually, this is not the first thing that will come to mind, but there's a little trick that I want to show you. It will make this code a little bit faster. You saw nothing. Okay. So we know that if we multiply two 16-bit values together, we can use the mul low function to give us the lower 16 bits of the result, and we can use the mul high to give us the high 16 bits. And mul high has two versions, by the way, unsigned and signed, because when you multiply two 16-bit values together, the low result is always the same, no matter if it's signed or unsigned, but the high result depends on whether it's signed or unsigned. It's weird. Don't worry about it. It's just, that's how it works. Okay. So multiply two 16-bit values together. In general, you get a 32-bit result. You can get the top and or the bottom with different operations. Now, here's a neat little thing. Multiply two numbers together, 16-bit values, where the low 8 bits are 0. What's it going to look like? The low 16 bits are going to be 0, and the high 16 bits are going to have, some value in it, depending on what was in A and B. Now, multiply two 16-bit values together. One of the values, the high 8 bits, have something in it. The other one, the low 8 bits, have something in it. What do you get? Well, if A and B are the same between these two, you're going to get the result here shifted down by 8 bits. Now this is kind of big, because what have we been doing so far? We've been multiplying two 8-bit values together. With mul-low, we get a 16-bit value, and then we shift that by 8 to give us our, our divided by 256 value. If we multiply with mul high, and one of the values is in the top 8 bits instead of in the low 8 bits, what we get is our result pre-divided by 256, pre-shifted. So we can save ourselves a shift operation if we skew one of our values over and then use mul high. That's the trick. That's the joke. You suck, McBain. Okay. So that's what we're doing here. That's what blend SSE high is all about. It's all about, see here, alpha and the complement shifted to the left by 8 bits. And then we call mul high EPU 16. It's got to be unsigned. And then in the end, we do the same thing. We add and we pack. But this saves us from having to shift. It saves us these shift operations. Shift isn't a super expensive operation. It's pretty fast. But still, it's going to be a little bit of a gain. So let's try blend SSE milliseconds. Now we're gonna blend here. Yeah, that's good. And we're going to go to the log file. Now we're getting 383. That is not an insignificant speed up. Over 20%, like 25% maybe. It's good. It's really good. Almost 25%. So it's not bad for a little simple trick. What else? Now, one little thing I want to show you. If I can remember where my code is. Here it is. Now AVX, I'm just going to do a little blurb on AVX. AVX is like SSE, only it works over 256 bits. And it's almost like executing two SSE instructions side by side, the same instruction side by side. And the funny thing is, you can basically take an SSE algorithm, a piece of code, a routine, if you will, and replace all the M128Is with M256Is, and replace all these MM128s with MM256s, and it just works. So it's almost the same stuff. It's all the same bullshit. Of course, you got some more constraints with respect to alignment stuff, because now you're working with data that's twice as wide, but in general, it just works. You just basically do a copy and replace, and you're all good to go. So let's try with AVX. And we're gonna zoom in, zoom out. That's not what you call that, but That's the words that popped in my head. And we see that we get a little bit of a boost, but not as much as you'd expect. You're not getting a 2 times boost. And I think the main reason for that is probably we're already maxing out what our memory can handle, what our cache, the speed of our cache. So in this case, AVX not gonna be a big help. But I could be wrong. There could be other factors. Like, for example, we're building this code 32-bit. If we switch to 64-bit, if we switch to using all AVX, because you get penalties sometimes for mixing AVX and SSE together. So if we switched all our code, like if we go into here, properties, what the fuck? Properties? Configuration, here it is. And C++, code generation, and we switch this SSE2 to AVX2, telling the compiler you can use AVX, and then we don't call any SSE instructions, and we use x64, then it might be good. It's not, the problem isn't with mixing SSE and AVX, it's with mixing VEX and non-VEX instructions, but I won't get into that right now, it's not important. What is important is that AVX gives us a little boost, but not too much. And I wouldn't expect too much because we're already pushing the memory limit. So, what's next on the plate? Blend half average SSE. Okay, so here we're just blending 2 images half and half together. It's the same as tinting, except instead of using just a fixed color, we're now loading pixels from 2 different images, averaging them, and then storing them back into one of them. It's the same thing. It's going to be fast. I mean, it's going to be super fast. Let's just take a look. Blend half average SSE. Okay, yeah, we don't need an alpha value, obviously, because alpha is fixed. It's going to be 127 or 128 or whatever. 128, I guess. So yeah, we got a nice blend there. And if we look at our good friend Mr. Log file, 334, 315, yeah. So basically, we're maxing out our memory more than anything, and that's why, yeah, that's why we can't get much better out of AVX. So blend alpha SSE. All right, so here's the last little section of my little ticketly talk. I don't know why I called it that. I don't know why I reverted to Mr. Ned Flanders. I don't even know why I called him Mr. I'm falling apart here. But so the way that the standard blend works is we're blending based on some constant fixed value that doesn't change between 2 images. But with blend alpha, we are now blending per pixel. So some parts of the image will be stronger and other parts can be weaker. And that can give you some nice effects, obviously, right? But it's also now we're adding more things that aren't fixed. So more processing has to happen per pixel. So let's take a look at what this looks at, because it looks pretty freaking sweet, if you ask me. So I've got an image with a proper alpha channel. It's called flare. So let's blend flare. And let's blend the flare alpha SSE high. So this is again using our trick of mul high with shifted values. As you can see, so here's our alpha image. We're blending that on top of another image. Most of it is just taking the source image, but some parts with the lens flare are strongly biased towards the alpha image, which is a lens flare. Okay, so I mean that's a neat effect, obviously. How expensive is it? It's pretty expensive. It's more expensive than standard blending 2 images without the optimization, right? So I'd say this is like maybe, I'm just pulling this number out of my ass because I don't want to pull out my calculator. Maybe like 40% more expensive than our optimized version of the standard blend. Alpha blend is more expensive per pixel alpha. So how is it different? I mean, we get our 0, again, we get our 1s. This is more just for my my own personal comfort. We load, of course, source destination. We got to unpack low and high from the source, unpack the destination. Then we broadcast the alpha. Now remember, because the alpha is now changing per pixel, we can't do it outside of the loop. We've got to broadcast every single pixel. That's what's adding some of the extra length to this this function. It's not giving us any girth, but it's giving us lots of length. We got to shuffle the low and the high. So I've put the shuffle low and the shuffle high into one instruction. So we call shuffle low, and the result of that will be the original source with the alpha values broadcast in the low, and the high values remain unchanged. And then we shuffle the high values, and then what we get in the end is just a value with all the alpha values. So alpha low, wait, where am I talking about? Source low contains 2 pixels. Source high contains 2 pixels. This shuffle will shuffle the alpha in the low pixel. This one will shuffle the alpha in the high pixel. And that's of the low 2 pixels. And then in the high 2 pixels, again, we shuffle the alpha in the low pixel and then the alpha in the high pixel. And what we get is we get alpha low, alpha high, each with 2 alpha values broadcast in 16 bits in the top and the low halves of the XMM register. Hope that makes sense. I don't want to draw a picture. And the complement is, again, we subtract from 255s. Then what we're doing here is we're shifting left by 8. And we're doing this in order to take advantage of our mul high bullshit. So we shift the source low and the source high by 8. And now we can, let me think here. We can do mul high and we get our results. So we don't have to shift down. Now there's a reason, remember before we didn't have to do any shifting whatsoever, but here we have to shift these values up for the source in order to take advantage of our bullshit. Now, the way it works is in the destination, notice how the unpack is switched. The 0 is now here and the destination pixels are here. And what this does is this will unpack it such that the channel values are in the high 8 bits instead of in the low 8 bits. It's weird. I fucking hate the way that Microsoft orders these what you call it, the parameters to these functions here. Because to me, I would think this would be the high 8 bits, this would be the low 8 bits, but no. Here, it's the low, these are the low 8 bits, these are the high 8 bits. So this is your standard unpack. You unpack your whatever you want into the low, and then you just put zeros in the high parts. This one, we switch it up. Now we're unpacking our values into the high 8 bits, and we're putting zeros in the low 8 bits. Now the reason why we don't do that for the source values is because we need them to be, what's the word I'm looking for? We can't have them all messed up because we have to shuffle the alpha values. Yeah. These alpha values have to be in the low 8 bits. So that means that these ones have to be in the low 8 bits. Because if we put them in the high 8 bits, then they will also be in the high 8 bits when we shuffle around these 16-bit values. So we can't have everything we want, and we have to do a little bit of shifting to get everything set up. But then we can multiply and add, and we can have a grand old time. And that is how babies are made. It's basically the same as standard blending, except that now we have to reshuffle the alpha values every time, every pixel. Now I'm going to show you some little bit of black magic that you would think does more than it actually does. So let's look at our good old friend Blend Alpha SSE High. No, we did look at that, right? And it was slow, I believe. Let's take a look at game. Yeah, it's kind of slow. Log file. Yeah, like about 580 milliseconds slow. Slow enough. Slow enough, my friend. Let's go back down here and look at the next thing, which is Blend Alpha pre-multiplied. Now, this is something that I didn't think of when I first did the tutorials in the alpha blending section, way back in intermediate maybe, or maybe even beginner, I can't remember. But what you can do is if you have like an image, like a sprite, that you're blending, alpha blending onto a destination, instead of unpacking the alpha from that image and multiplying it in every time, you can do that ahead of time. So you can take you can take an image with an alpha channel, and you can scale the channels of the image by the alpha, pre-scale, pre-multiply it. And if you pre-multiply and divide, of course, by the alpha, then all you have to do is do the same for the destination when you're doing the actual processing, and then add them together. So what we do is we load source, we load destination, we unpack the source and the destination. And then what we do is, like normal, we shuffle the alpha values into place. We broadcast them to where all the channels are. But now all we have to do is multiply the destination by the what do you call it? The complement. Then we pack it together, and then we add that to the source directly, because the source is always already pre-multiplied. Again, we don't get any overflow. It's just like when we were doing the packed versions of tint and whatnot. So by pre-processing, by baking our images, we can save some processing time. And let's take a look at how much we save. Because we are cutting out, I mean, if you look at this compared to this, we're cutting out a lot of stuff. We're cutting out multiplies. Multiply is a slow operation compared to the other ones we have here. So let's take a look. What is this called? Copy that. I should have been doing this the whole time. Paste it. Build. Run. Oh, it looks ugly. Why does it look ugly? Because I have not pre-multiplied the image. So we got to go here, uncomment this line, pre-multiply alpha. All pre-multiply does is it goes in here and it does the bullshit of scaling by the alpha value. And it also turns the alpha into the alpha complement, so we don't have to do that either. So it pre-scales by alpha, and then it pre-complements the alpha value. And then we have a baked surface. And if we bake our surface first, then we get a nice image. Very nice. And then if we look at this log file, we see that we barely get any speed up at all. We get a very little speed up. And you might be saying, Chili, that doesn't make sense. You've actually saved yourself quite a bit of bullshit here. Why isn't it much faster? Let's take a look at the situation. My situation is this. So if we've got some code like this, we expect it to execute these instructions one after another. So it moves the data, and then once that move is done, then it pushes it onto the stack, pushes EAX, call, move, does a multiplication here. Once that's done, it does a load. But that's not exactly how computers work these days. I think I just broke my computer. Okay, stop that. So computers are pipelined. And the reason for that is like an instruction, any instruction, it takes a number of operations to complete that instruction. You've got to fetch the instruction, you've got to execute it, you got to write the result back to memory, you got to decode the instruction. You got to figure out what those numbers are telling you what to do. And these instructions, all these operations, they take time. So let's say it takes 5 cycles to do an operation. So if you had 5 operations, you would imagine, okay, that's 25 cycles. But each of the steps in completing an instruction, these steps, let's say they're operating on different units inside of the CPU, different modules. So first, if you're executing instruction 1, you're going to do some processing in F, you're going to do some processing in D1, D2, EX, WB, and then the instruction's done. But that's kind of wasteful. Think about it. You do an operation in F, and then you move to do the next part in D1. F is just sitting there doing nothing. D2, still sitting there. D3 or EX, still sitting there. And then you can do another operation here. It's wasteful. You don't want to have all these units sitting around doing nothing. So what you do is you pipeline your instructions. You break them down into the steps that can be executed on different units. And then you do step 1 in F, and then step 2, D1. Now F is free. F starts the next instruction. So F is going to be working on instruction 2, D1 is working on instruction 1. Now that's done. Now D2 is working on instruction 1, D1 is working on instruction 2, and F is working on... Now I'm getting all confused. Just work with me here. It's all good. When you get to this point here, all these units are now going to be occupied doing some work. And instead of 5 instructions taking 25 cycles, now they only take 1, 2, 3, 4, 5, 6, 7, 8, 9 cycles. And that, my friends, is very nice. So, what does this have to do with our pre-multiplication optimization not doing it for us? Well, every instruction here has two main performance values associated with it. And those values are the latency and the throughput. Now the latency is how long it takes that instruction to finish. Basically, if you look at that in terms of the diagram I just had up, if I can find it, latency means the number of boxes here, basically. So it takes 5 cycles from the start of the instruction until the result of the instruction is available. Now, let's go back to our thing here. Throughput is how many of these it can execute per clock cycle, or the inverse of that. It's kind of complicated. I don't know why they give you the inverse, but basically a throughput of 1 means you can execute 1 multiply per clock cycle. So you can start a new multiplication instruction every single clock. So that's basically almost exactly like this diagram here. One instruction takes 5 cycles to complete, and you can start a new one every single clock cycle. So you get a situation like this. If you look at other instructions, let's go back here, like the one I had before, if I can get to it. And if I type in and, why do I get add? That's weird. Now and is very simple. It has a latency of 1, so its value is available almost immediately. It has a throughput of 0.33, which means, strangely enough, that it can do 3 of these operations every clock cycle. It can start 3 of them every clock cycle, and the result is available in the next clock cycle. So it's a super cheap instruction, whereas multiply is pretty expensive. If you want a really expensive one, then try mul packed single. Wait, that's fine. Okay, let's try what is it? Div packed single. So now this one has a latency of 14 and a throughput of 14. So you can, well, it depends obviously on the chip. But in Sandy Bridge, it's the worst, so I just picked that. So it takes 14 cycles for the value to appear, and you can get 1 instruction every 14 cycles. So there's almost no overlap. It's very slow. Division in floating point is very slow. So, that being said, what was I talking about? Okay. So the important thing, the 2 important values for an instruction are the latency and the throughput. Now, these values come into play in different situations. If you've got a situation where you're doing a calculation of x1 times y1, x2 times y2, x3 times y3. These can all happen at the same time. So you're mostly interested in the throughput. How many of these can I push per clock cycle? But if you're doing an operation like x1, like let's say this is z1 is equal to x1 times y1. Now if you're doing an operation like x1 is equal to x2 times x3, and then x4 is equal to x1 times x5, and then x6 is equal to x4 times x7. The numbers are weird, but you get the idea here. If you've got x2, x3, you multiply them together to get x1, and then you've got an x5, you multiply that with x1 to get x4, and then you've got an x7, you've got to multiply that by x4 to get x6. So you see here, the value of this operation here you can't get it until you've completed this operation. So now you're worried about the latency of this, the latency here, because your operations depend on the values that were subsequent to them, the subsequent operations. So this is latency bound. You've got a what's called a chain of dependency. And this makes code slow, because now instead of being able to issue 1 multiplication per clock cycle, you're basically limited to 1 every 5 clock cycles because you're waiting on these x values. Now that you understand this, take a look at the code again and maybe you'll see why we didn't get much of a benefit from eliminating 2 multiplications here. Let's go back down to blend alpha pre-multiplied SSE high. Here we go. So in our standard blend alpha, we're doing 4 multiplies. We're doing 2 shifts and 4 multiplies here. In this one, 2 multiplies. So we've eliminated a couple of multiplies and maybe a couple of shifts as well. But shifting is super fast, so it doesn't really matter. Now the thing about eliminating these multiplies is look at these 4 multiplies. Source low 16, alpha low. Source high, alpha high. Destination low, alpha low. Destination high, alpha high. And they're going into result, 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 result. If you notice, all of these 4 multiplications can happen in parallel. They don't depend on each other. So even if we eliminate 2 of them, they were happening almost in parallel anyways. So we didn't really eliminate anything from the dependency chain. We just eliminated 2 operations that were already happening in parallel. And that is why we don't get the speed up. And this is a very big thing in optimization, identifying dependency chains, operations that depend on each other, and trying to make those chains as short as possible. And the length of the chain is determined by not really by the number of instructions, but in the latency of the instructions. Latency adds to the length of the dependency chain. Throughput gives you more girth in your parallel execution of instructions that are not chained. It's the old length versus girth question. It's a one for the ages. But anyways, so that's the reason why pre-multiplied is not giving us the boost that we would have normally expected from eliminating, eliminating 2 multiplications and eliminating these shifts. It's kind of a disappointment. But it is what it is, as people say. I don't like that saying because it doesn't actually say anything. It's a tautology, right? It is what it is. Well, yeah, fuck, of course it is what it is. Are you fucking, Anyways, so now I'm going to show you something that will give us a speed up. And it is going to make use of a little something that I like to call SSE3. I didn't make it up myself. That's what it's called. It's actually really stupid. This isn't a typo. There is a SSE3, and then there is a SSE3. It's just don't get me started. But this will allow us to use one instruction called shuffle EPI8. And this allows us to shuffle 8-bit values across the whole register. It allows us to shuffle 16 8-bit values anywhere we want inside the register. Now this is beautiful because we don't have to do shuffle high, shuffle low anymore if we do this stuff. What we can do, let me just show you. We gotta have shuffle. Oh, there it is. So the instruction is pshuff-b. Now, if you remember what I said before, SSE is limited in that the immediate operand can only have 8 bits. And so, for example, that 8 bits would allow us to shuffle 4 values into 4 arbitrary positions. But now we're shuffling 16 values into 16 arbitrary positions. That's going to require a lot more bits, right? Every position is going to require 4 bits, right? 16 positions. And there's 16 values. So that's 16 times 16. Wait, no. 4 bits times 16. 4 times 16 is 32. So we need 64 bits. And that is not going to fit in our size that we have for immediate values. So what we do instead is we use an SSE register as a shuffle mask. And so all of our shuffle values are now held in another SSE register. So, for example, What is love, baby don't hurt me? No. What is 0D, 0A? Okay, I get this. So this is the mask. This is what's telling us what value to take from. So position 0 of the mask determines position, what is this? Oh, 0, okay. So position 0 of the mask determines what goes in position 0 in the destination. So position 0 in the mask says 9. So we look at position 9 in the source, FA. That's what goes in the destination. Do you get it? The top position of the mask says 0D. We look in D, it's a 65. We put a 65 in here. These ones all say 0A. So in these positions here, we're going to take the value from 0A and broadcast it in. That is the magic of, the instruction is called P shuff B, packed shuffle bytes, and the intrinsic is shuffle epi 8. And it's fucking sweet. It's just so good, and I can't even begin to tell you because there are other applications to this. The rabbit hole goes so deep you don't even know. But the basic important thing is that we can freely shuffle 8-bit values anywhere inside of here. The only cost is it takes a register to do it. And remember, whatchamacallit, SSE instructions, they only have a source and a destination register. So what it does is the destination is actually the mask. So by shuffling, you destroy the mask. These values get replaced with the shuffled values in here. The mask is destroyed every time you shuffle. So you've got to rebuild it every time. You got to recopy it, whatever. So that's one downside to P shuff B. But it's so good. It's good. It makes my dick so hard. Anyways, so by using this, we can save on shuffle high and shuffle low. We can do that all in a single operation. So here we got the source pixels. Now we've got to build our shuffle mask. Oh, one more thing I didn't tell you. It's not in this diagram. But values from 0 to 16, or basically it takes the low 4 bits, 0, 0, 0, 0. It takes the low 4 bits of every 8-bit value in the mask, and it uses that as the index for shuffling. But it also looks at the very top bit, so the very top 8th bit, and if that bit is set, it doesn't shuffle, it just sets the motherfucker to 0. So it also can selectively clear out areas, not just shuffle. Also clear. So good. Makes my dick so hard. So here we're going to shuffle, and these shuffles are for broadcasting the alpha to the places that we want. So 128, that's the top bit is set. We're clearing the top bytes, and we're setting the low bytes to the value of the alpha. So the alpha value is in the 4th byte, which is byte 3, right? Because we start from 0, 0, 1, 2, 3, and the 7th byte. And we are shuffling that inside. Right. So we're shuffling. What this lets us do is this lets us unpack and broadcast alpha at the same time, right? Because we're shuffling from packed pixel values. So from 4 pixels, which are packed into 8-bit channels, we are shuffling, unpacking by setting it 0 value, 0 value, 0 value. This is unpacking and broadcasting the alpha at the same motherfucking time. Unpack and broadcast at the same time. It's so good. So obviously we still have to unpack our channel values. So we unpack those. We unpack the destination. We load the source the way it is, right? Because we're dealing with pre-multiplied values. We don't have to unpack. We just add the source. Destination. Yeah, we don't have to unpack the source. So we load the source, load the destination, unpack the destination. Then we shuffle unpack, so we broadcast unpack the alpha values. And these are the complemented runs, right? Because we've cooked this surface. Then all we have to do is do the mul high bullshit. We pack, we add, and we store. This is much less than this. And this, I'm not going to draw the diagrams because I don't have much time. I mean, I have all the time I want, but I don't want to make this video so goddamn long that you'll die of old age before you finish it. So what I'm going to do is I'm going to be smart. I'm going to copy this. I'm going to paste it in here. I'm going to look at the performance we had, 5.5. Then I'm going to run this. Still same old G, you know me. And now we're down to 3.85. Very nice improvement in speed. But there is, one catch. And the catch is... Where's my motherfucking... The catch is that this is SSE3. So somewhat old processors will not support it. So you have to check to see whether the processor supports SSE3 before you use any of these instructions. Otherwise, your program's just gonna shit the bed, obviously. Now the way you do that is there is a special instruction on x86 computers called CPU ID. And what CPU ID does is it gets a bunch of dumb information about the CPU. All of what instruction sets it supports, the name of the vendor, and the name of maybe the brand. I don't know. It's all in here. Anyways, I didn't write this code. I just got it off of the MSDN and copied it into a CPP file and an H file. But you can use this code because I use it. And it's very nice. Very nice. It has one static instance, like a singleton, that it creates automatically in, where is it? In here, instruction set. And all you got to do is then just call instruction set blah, and you can get information about your CPU. So what I would do here is I would do something like if instructions, okay, that's not working. Let's change our strategy here. We're going to include CPU ID. Get rid of that and that. So, very simple. You can use this file whenever you want if you ever need it. It's not mine. I didn't make it. But yeah, if you're going to be using... I mean, you can basically assume that any processor supports SSE1, which is, Pentium 3 and higher, and SSE2, which is Pentium 4 and higher. I mean, if they're running shit on a Pentium 3 and it don't support SSE2, it's just like, what are you doing with your life? So, but when you get up into like SSE3, I've had people who couldn't run my code because the CPU that they're using doesn't support it. So you can't make assumptions like that, especially when you get up into like AVX and stuff like that. That shit... Now, there's plenty of people who don't have CPUs that support that. So you got to check that stuff. And you check it, well, you just use this class, code, whatever. But anyways, that is all I want to talk about today. I think we've covered quite a bit. Dependency chains and instructions and bullshit. And this is all basically, what this is I'm getting prepared for... the Hugs series, where I'm going to make a very nice full screen bloom filter, all in software, all using SSE. Very fast, very beautiful. Make your dick so hard. Diamond Dick, as they call it. But anyways. Oh man, I just zoned out there for a second. That's it for the episode, and I will see you soon. And the next one will be the last in this part of the SSE series. I might do another SSE series. I might do one especially covering floating point SSE. But the last one is going to be the end of the first arc of SSE, and then we'll see. But yeah, thanks for watching. I hope you learned something and enjoyed the video. And if you did, click the like button. It helps out a lot. Leave a comment, ask questions. You can ask questions on the forum, in the comments. It's all good. I will see you later. Hey everybody, welcome back. I am Chili, and this is Lesson 4 of the SSE Hand Relief series. That's a Borat reference, by the way. Today we're going to be talking about alignment. And alignment is one of the things I like to classify as dumb bullshit. Now, there's a lot of stuff that I say is dumb bullshit, but this truly is the dumbest of all the bullshits. Now, let us waste no time and get started here. Now, one thing you might have noticed about the SSE series up until this point is every one of the filters that we've been working with, they've all been full screen. And this is by design, because if you have a full screen filter, you don't have to worry about alignment, because everything starts at the beginning of the surface, and as long as the surface was allocated such that it is aligned, then your full screen filter operations will all be aligned as well. However, if you want to do something on a smaller region of the screen, like for example, you want to draw a rectangle, an arbitrarily sized and positioned rectangle somewhere, you are in general not going to be working with aligned pixel values in the start of your drawing. And that's going to cause you problems because, as I've mentioned before, SSE likes to have its stuff aligned 128 bits or 16 bytes. So let's get a little start on this tutorial. We're going to try to draw a rectangle using very simple algorithm here. Draw rect SSE bad. So simple, very simple. Takes a rectangle structure, a reference, constant reference, and a color. And then it draws the color to that region on the screen. So all we're going to do here is we've got our outer loop, which is just looping the Y variable. Our inner loop, which is looping the pointer that goes along every row. And then we're storing 128 bits at a time. Quite simple. I hope I don't need to explain all that at this point. So we go graphics.sysbuffer.drawRect SSE bad. We need to give it a rectangle. So let's go with something simple. I think my rectangles go left, right, top, bottom. So 16, 32. Let's go 32, 64, and we'll go 50 to 101. Some random numbers there. Not quite as random as all that, but still. And the color we'll use is a nice green color. I'm feeling green today. So we'll build that and we'll see how it goes. Start without debugging. And as expected, we get our nice green rectangle here. Top left-hand corner. That's all good. What if we try to shift over this rectangle by just 1 pixel to the right? I'm going to put this in debug mode and run it again. And what do we get? We get access violation, reading location, blah, 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 blah. Break. Why? Because we are trying to store to an unaligned memory address. I don't know why it says access violation reading from. It's probably some bullshit that the debug code puts in there. But at any rate, the problem lies in the fact that we are not aligned. So, what can we do to get aligned? Well, if we look at, let's take a look here. Imagine this is our a row of pixels that we're writing to. Note that alignment, the Y direction doesn't matter at all, right? That doesn't make any difference. It's only the X direction that you have to worry about alignment in. Because the Y is just separate rows, and every individual row is always going to be aligned. It's just the pixel in an individual row, whether it's going to be aligned or not. Not the pixel, but the 4 pixels. You get what I'm trying to say. The group of pixels. The double quad word, I believe is what you call those. But anyways, so let's say we're going to try to draw this row of pixels into a surface, into memory. So I've got these pixels labeled. This is not the byte count. This is not the pointer values. This is the pixel count. So every 4 pixels here is actually 16 bytes. Well, we don't have to worry about that. We want to align to every 4th pixel. So what we're going to do is, if we try to draw, like, this is the thing that we're trying to draw here, the line or whatever you want to fucking call it. It is 8 pixels wide. So that is 2 SSE store operations. Correct. So far, so good. Now, if we try to do that, if we try to store, first we'll try to store this one. The problem is we are not storing to an aligned section of memory, so we're gonna get our program is gonna crash. It's gonna shit the bed, as I like to say. So, what do we do about this? The solution is quite simple. It has a name, and the name is called, what's it called again? Loop peeling is what it's called. Loop peeling. So what loop peeling is basically breaking up a loop into several smaller loops such that shit works correctly. Specifically, in our case, this part of the storing and this part of the storing here is not going to be aligned. This part, the middle part, will be aligned. So what we do is we break down the storing loop into 3 loops. First, in the pre-loop, we store this single pixel. Then in the mid-loop, we do an SSE store. This store here is just normal. So this would be scalar, vector, and then here's a loop of 3 stores of scalar pixels. And if we do that, then we're all good. We don't have any problems. What does that look like in code? Well, let's take a look at direct or draw SSE without the badness. And we see we have 3 loops here. So we calculate, what do we calculate here? Let me just take a look at what I have written many moons ago. So we're going to calculate some pointer values. These are end peel, end loop. Why do I have it like this? I don't know. Start loop. What do we got here? Okay, so actually the function starts up here. I wasn't even looking at this part here. So what are we going to do? C128. So we create a, this is the same as up here, right? Yeah, we just take the color value and we fire it into all 4 color positions in the XMM register, the SSE register. That's no problem. Here, we want the start of the loop, the end of the loop. So this is finding the start of the aligned portion and the end of the aligned portion. Could have named these variables a little better, like start aligned, end aligned, but whatever. Doesn't matter. So here, what we're doing is we're adding 3, and then we're taking the modulus of 4. This is a fast way of getting the modulus of 4. Or this is the fast way of getting the modulus of 4. So what we do is we add 3 to bump it up to the next value, and then we drop down to the mod 4. For example, taking a look at this. So here our position is 3. We add 3 to that. 1, 2, 3. We get 6. And then 6 mod 4 equals 4. So this finds, from any starting position, it finds the beginning of the aligned portion. And the same with this one. Here, what do we do here? Let me take a look at our good old friend. Yeah, here. We just, we end with this value here, and that drops it down to its nearest 4th aligned position. So this here, it's not like I said before, it's not mod 4. It's rounding up to the nearest, if we add 3 and then end with this, we round up to the nearest 4th aligned position. And if we just end with this, we round down to the nearest 4th aligned position. So we're just, basically what we're doing is we're taking the whole range here and we're squeezing it down to just the aligned portion. We're cutting off the unaligned end trimmings, if you will. All right, so P end peel here is calculating the end of this first loop here, which just handles the trimmings on the beginning. And so we calculate the end of this loop, and for some reason that I can't understand, I also calculate the end of the vector loop here. And then we start the peeling loop at the start of our rectangle, and we're going from the current value until the end, and we just increment the pointer, and we store our color into the memory there. Very simple. Now here, what we're doing is we're going to cast our values to SSE pointer values, and we're going to go from we're going to start at the end of our last loop, the P end peel, and we're going to go to the end of this loop, and we're just going to increment the M128 pointer, and we're going to do vector stores, and then at the end we're going to start at the end of this loop, and this loop is going, let me think here, what is this? Oh yeah, so this is pointer to P current, and the end of this loop is going to be the end of the rectangle. So just the rectangle.right, which is the X value, plus the pixel pitch times the Y of the current line that we're writing. And yeah, again, same, just a bunch of pointer bullshit, pointer arithmetic, because it's faster, but it's also harder to read and a little more difficult to write, which is why I only do the pointer bullshit on the inner loops, and on the outer loop I just loop on the actual index, or the actual coordinate, the Y coordinate. So let's take a look at how this runs. Remember, this SSE bad crashed on this code. Let's see what SSE not bad does. It works fine. No problem. Because we handled the unaligned portions at the beginning and the end of the rectangle with loop peeling, we have success. We have succeeded. Very simple. So that wasn't so hard, right? What was Chili talking about all this dumb bullshit? I don't see bullshit that is quite that dumb. Well, wait first, because we've got lots more to go over here. What we've got here is now we're going to try to blit from one surface to another surface. So we're going to try to copy. This would be surface 1. This would be a single row of pixels for surface 1. And here is a corresponding row of pixels in surface 2. And we're going to try to copy from here to different locations, just as you would generally do in a blit operation. Now, the problem with this, well, let me illustrate with some fancy drawings. So, what we might want to try is, okay, well, loop peeling worked great last time. Let's try that again. So what we'll do is we'll draw this pixel here. We'll draw it with just your standard scalar operations, and the end pixels here we'll also draw with scalar operations. And now the internal part, the aligned part, we can just load this with SSE loads and then store with SSE store. Only, oops, we can't do that because, well, I mean, look at it. If we load this block here, this block corresponds to, let me just get some different color here. That corresponds to these pixels here. This goes to here. But if we try to store this with SSE store, we'll get, you know, our compiler is going to puke. Not our compiler. Our compiler won't give a shit, but our computer will puke because it can't store to this unaligned address. Not for SSE. So you might say, well, Chili, I got you. I know what we got to do here. Before we had only one surface, the destination. So all we had to do was peel for the destination. But now we've got the source and the destination. So what we got to do is we peel for the source, and then we peel for the destination. Well, let's try that. Let's peel at the destination here, and we got to peel this off here. And so this will now be scalar stored as well. So we're going to do that, and we're going to do that. And oh shit, well, now we've got this aligned bit here, but the corresponding source is again unaligned. So you can't use peeling to solve this problem because the source and the destination are unaligned to each other, if that makes sense. They are out of phase, so no amount of peeling is going to correct that. It's not just a problem of fixing up the ends and then you're good to go. The problem lies throughout the whole operation. And so you're not going to be able to just fix up the ends and Bob's your uncle. That's what I'm trying to say to you. So what you got to do is, let me think about how I want to word this, how I want to explain the situation. Well, let's take a look very simply at, screw that. Let's take a look at what you would have to do to store to a single position here, to a single aligned position in the destination. So this will be our base. Okay, let's say you want to store to a single aligned 4 pixel location here in the destination. So what source pixels correspond to these 4 destination pixels? Well, we've got 2 pixels here, so we got 2 pixels here. So that means that these 4 pixels correspond to these 4 destination aligned pixels. So what you're going to do is you're going to load these 4, and you're going to load these 4, and you're going to combine them to create these 4 here. So let's take a look. Let's give them names. We'll call this one A, B, C, and D, and we'll call this let's see, W, X, Y, Z. Now, our final result is going to be B, C, D, W. So how do we get that? Well, what you do is you load A, B, C, and D, and you're going to want to shift this one left by 1 pixel, so by 4 bytes, and that'll give you, so shift left 4, and that'll give you B, C, D, and nothing, 0, empty, nada. Now for this one here, W, X, Y, Z, we're going to shift this one right by 1, 2, 3 pixels, which is 12 bytes. And that'll give you 0, 0, 0, W. And then what you want to do is you bitwise and you bitwise OR these together. And bitwise OR 0 and anything is just your anything. So you're going to get B, C, D, W, which is what you want. And then you can store this directly in your result position. And that's about it. And what you do then is you say this is your say this is your old, this is your new, okay? So you combine old and new with some shifting and ORing, masking if you will, to get the combined result, and you store that. Then this is, don't need this anymore. New becomes old, and your next 4 pixels are now new, and you do it again here. And you just keep going along until you get to the end. Now, the beginning and the end are a little different. All right, so let's take a look at some simple situations for blitting with SSE. So the simplest that you can conceive of is the source and the destination are both aligned. So your source rectangles, your left and your right, are aligned, and your destination point, the X value, is also aligned. So all you got to do then is you calculate your pointer for your source, your end pointer for your loop, which is just your pointer for your source, plus the width divided by 4. And you're dividing by 4 because your loop is going to be looping on, your source is a 128-bit value, so that's 4 pixels, but your width is just a single pixel value. So you got to divide by 4 to get your width in SSE chunks. And then you add that SSE chunk count to your original pointer to get your end pointer. And the destination, again, is just simple calculation. We've done this all before. And you do your load and your store, and it works fine as long as both your source and your destination are aligned. However, if they're not aligned, bad shit happens. So the next simplest situation that you can look at is the source aligned situation. Now in this situation, we assume that your source rectangle is already aligned to SSE memory requirements. So in that case, all you've got to do is handle the alignment with respect to the destination. So what we do here is we mod the destination point X by 4, and then we use a switch statement, and we just change what we're doing depending on the alignment value. So in alignment 0 means that the destination is also aligned, and then we just do this stuff here. All I did was I copied this body basically into here, and that was it. Now for the other cases, we don't have alignment, and so we've got to do the stuff I was talking about before, which is to say that we here we're looping through the Y values, and so here we get pointer to the source, divide by 4, round down. So what we're doing here is we're not really, it's kind of loop peeling, but it's not really. Yeah, it's a bit of a doozy. Well, the source that we're loading here is just going to be the actual pointer calculation. There's no adjustment going on because this is source aligned, as we stated up here, blit source aligned. So there's nothing fancy going on here. Just load the pointer to the first pixel. And the end is again just divide by 4 to get the chunk count of the width. Add that to the starting pixel pointer to get the end one. Now the destination, we have to in this one we're rounding down to the nearest 4 aligned address. And again, we use this to round down to the nearest 4. And then we start our bullshit. Now what's going on here, the idea is we're going to start storing to here. So, well, this isn't actually correct because our situation as it stands is more something. Gotta get rid of all this bullshit here. Excuse me while I adjust my diagram ever so slightly. So our source is aligned. Our destination is not aligned. So our destination is just going to be up to here. And this is actually nothing. So forget about it. There. Beautiful. All right. So our source, we're going to start loading from here. We're going to do 2 loads and we're going to store. Now the problem is we can't just load this and store it to here because that's not the way it is. These pixels belong here and these pixels belong here. So what we're going to do is we are going to prime the pump, as to say, to get our engine started here. We're going to load the original value of the destination here. So let's say that this is A, B, C, D. We're going to load this one here, and then we're going to shift it right. Here we have alignment, destination alignment of 2, right? This would be 0. If it was here, this would be 1. This is alignment value 2. So we're going to shift right by 2. We'll get 0, 0, AB. And this is W, X, Y, Z. So now what we do is we load W, X, YZ. And then we proceed, as I mentioned before, in that this one is going to get shifted left by the alignment value, which is 2. So we'll get AB 0, 0. This one is going to get shifted right by 4 minus the alignment value, which is also 2. So we'll get 0, 0, WX. Then we will OR them together, and we will get A, B, WX, which is what we want in here. We want the original values here, and we want the blit values in here. So we composite this original block and the source block to get the final destination block here. And then we proceed as before. So this was new. This value here, the pre-shifted to the right value, was old. Old gets discarded. New becomes old. This becomes new here. And we'll get G, H, J, K, I don't know, whatever. And so then we will, for this one, shift left by 2. We get YZ. This one, shift right by 2. We get 0, 0, GH. We OR these together. And that gives us YZ, GH. And that's what's gonna go into here. Y, Z, G, H, which is what is supposed to go in there. So, and then pump continues. Discard this. This becomes old, and this becomes new, only we're done, so we don't actually need to do that. But that's the general idea. Now, at the very end, we have a problem here. And the problem is we're going to store JK into here, but we have to leave these values the same. And we handle that basically the same as we handled the beginning. We first preload the destination values into a register, and then we composite them with the source values and write back to the destination. So that is how it is done. So here's how it is actually done in code. The first part that I talked about, I call that priming the pump. And so we, our old and our new is going to be, what is it going to be? Previous and new source. So we got previous source and we've got new source. So we load the first, in the beginning, previous is going to be the destination pixels. And they're going to be shifted left by 12. This is case 1. So we're shifting these ones, pre-shifting them left by 12. Does that make sense? I think it makes sense. I'm going to say it makes sense because it works. And then when we enter the loop here, this is where we do the actual writing. We're going to load the new source from the source. And we're going to combine the previous source shifted right by 12 and the new source shifted left. Okay, I understand now why I'm getting mixed up. And I always do this bullshit. It's something that I fucking hate. But when we write pixels onto the screen, the lowest pixel here is going to be on the left. And as you go right, the pixel values increase, right? The pointer values in memory increase. But shifting right means shifting to the low side. So this, if you have a value or register of 4 pixels that you loaded from memory and you shift it right, you're actually moving the pixels left on the screen. Because when you write a binary number, right, 0000001, this is the low, this is the high. So the high goes on the left. But when you're actually drawing pixels on the screen, the higher order pixels go on the right. So it's opposite, and that's what fucks me up. And I have written so many freaking bugs into my code because I got my right and my left mixed up. So Chili can't tell left from right. That's the moral of this story. Don't do like Chili do. And so when you want to move pixels left, you shift right. And when you want to move pixels right, you shift left. It is seriously dumb bullshit, as I've stated before, but it has to be done. So that is why we are shifting left here to prepare our pixels, prime our pump. And then when we actually put them together, we shift right, we shift left, we OR them together, and we store. And we keep doing that until we get to the end of the aligned portion. And when we're at the end of the aligned portion, previous source is going to contain the last block of source pixels loaded. And what we're doing then is we're going to combine that previous source with the pixels that are here to get the final block to be stored. And that is done basically like this. We have to load the destination pixels, and then we shift right, and then we shift left. And what shifting right and then shifting left does is, if we refer to our diagram here, our final destination block is going to contain, pixels A, B, C, D, but we only want C and D. So by shifting right, and this is shifting right, and then shifting left back, we end up with something like this, 0, 0, C, D, which is what we want. And then we shift our old values. Where do we shift them? We shift them right to get them over here, and then we OR them with this. And yeah, here we go, shifting right by whatever amount we need to, and we OR them with the right left shifted destination values, and we get our final value to be stored. And that is how you process a row when the source is already aligned, but the destination is not aligned. You break it down into 4 cases, and you process those 4 cases. Now, this is very nasty. We've got a lot of repeated code here. In fact, the only thing that changes really is these shift values here. This value 8 here, and down here, the value is going to be 4, 4, and basically the complement, which is 12, right? 4 plus 12 equals 16. Here it's 8 and 8 because they're the same. Here it's 12 and 4. You get the idea. That's the only thing that's changing. So you might say, well, Chili, why don't you just make a function for all of this code here? Make a function where you pass in the alignment value, and then you can do your bullshit. And there's a problem with that, and that is that these functions here, for example, the shift left, this value has to be a constant that is known at compile time. The compiler has to know this number while it's compiling. It can't be a number that is derived at runtime. But function parameters are derived at runtime. So it's not compatible. You can't write a standard function to do this bullshit because it contains values that have to be known at compile time. Now, C++11 has something called constant expression, which is a way you can specify a constant value whose value is known at compile time. But the compiler that I'm using right now, or the environment, which is Express 2013, has not yet implemented that feature. That feature comes in, I believe 2015 has it. So, without using constant expression, how do we do this? How do we do this dumb bullshit? That's the question. Now, the answer is there's a trick you can do, and the trick is called use a template. So here, I've got the same thing here, the blit SSE source aligned, templated, and it basically breaks those things up into functions and calls them. But as you can see, the alignment value, like I said, you can't pass it in a function parameter. But what you can do is you can use a template parameter to instantiate a template function at compile time, and that template parameter will be inserted as a constant that is known as at compile time, and then everything works. So what you do is, well, let me show you. Well, first of all, for the 0 case, all I did was I called the function that I wrote up here, which is draw blit SSE source destination aligned. So this is the case where everything is aligned perfectly. You just got to copy. So I'll just call that function here for case 0. Now for the other cases, I've got to do bullshit to align. So I got to prime the pump and all that other fun stuff. So what I do is I go down here and I create this template and I give it a parameter, which is an int parameter for the alignment. And this template function is a wrapper around the other one. All this one does is it contains the while loop, which loops through all the stuff here. And then for every row, it calls this one source aligned row template with the alignment. It passes this alignment parameter down to this template function. Go to definition here. And this one just has all that other stuff I explained before. So here you've got the alignment value. And that value, we multiply by 4. Where is it? I can't find it. Here we go. We multiply the alignment by 4 to get the left shift value for the new source. And we take the complement, the 4's complement. I don't know if that's what you actually call it, but that's what I'm going to call it. And then we multiply that by 4 to get the shift value to the right for the previous source. And that's also the shift value here for the priming, the value priming bullshit here. So that's what we're doing. And this makes the code, you know, a lot nicer. And if we make a change to the algorithm, instead of having to change every instance in the switch statement, all we've got to do is change the template function, and that changes every instance already. So that is how we'll generally proceed when we have to do this dumb bullshit with constant expression values that we need. But in the future, when I switch over to 2015, someday I would like to try out the constant expression without this template shenanigans. That's a word, right? I don't know. All right. So that is the case for when the source is already aligned. Now here, we do the same thing, but we use SSE3. And SSE3 gives us a nice function. Let's go to definition here, and we'll go to definition here. Take a look. So it gives us a function called alignR epi8, which is which emits the instruction p-align r. And what that does is that allows you to align two XMM registers together. So basically what it does is it does all of this shifting and masking bullshit, and it does it all at once for us. So let me just bring out a nice little layer. So let's say we've got two registers. We'll call them A, B, C, D, and W, X, Y, Z, and we go p-align R, and we do some, let me think here. We'll call this one G, we'll call this one H, and we do p-align R, G, H, and 8. And what that'll do is it concatenates G and H together, A, B, C, D, W, X, Y, Z, and then it takes an offset from the beginning here of this number here. So 8, the offset would be here. And it gives you the 128-bit value, which is in this window here. So the offset value slides this window around. And these two values determine what values make up the 256-bit concatenated value. So it allows you to basically slam two values together and then get any 128-bit window inside of your 256-bit concatenated value. So it does all that shifting and masking bullshit all in one shot, which is great. If you have it, it makes your alignment bullshit faster. But otherwise, this is exactly the same as what we had before. And it does the same bullshit. So that's just the SSE 3 version of that. Source aligned templated. SSE 3 source aligned templated. So now we get down to the thing that I wanted to do, which is I want these ones up until here, they have assumed that the source rectangle is pre-aligned. What we want is a function that makes no assumptions, that can work with any source, any destination. You call it, it just works. And that's going to require some extra bullshit. All right, so the first thing we do is we check to see whether our source is less than 4 pixels wide. Because if it's less than 4 pixels, we can't even get a single SSE transfer in there. And in that case, all we're going to do is just pass it on to our standard blit function, which, doesn't do any vector transfers or whatever. All it does is a very simple loop, and it copies the pixels. So if we're so tiny that it doesn't even matter, just call the standard function and be done with it. Now, if that's not the case, what we're going to do is we're going to check our source alignment on the left side and our source alignment on the right side. So this is basically doing is just rounding up and rounding down to the nearest 4 aligned x coordinate. And then what we're going to do is we're going to check to see if the original left and right are the same as the source aligned left and right. And if they are the same, all we do is we call our previously determined source aligned templated function. So if the source is already aligned, we can just call this simple function that we've already defined, and we'll delegate to that one. Now, if the source left and right, or either one of them is not aligned, then we first have to align the left and the right before we can call those functions. So then we first we get the alignment value for the destination x. Now I don't know what this thing here is for per se. This is adding to x So this is the alignment of the destination after we have peeled away the unaligned parts of the source. So the difference between the aligned source X and the original source left is basically the width of the amount, the portion that has to be peeled. So we add that width to this X here to get the start in the destination of the source part that is aligned. Does that make any sense? It's kind of complicated. So that's this calculation gets the start in the destination of the aligned start of the source. And this thing here just gets the alignment value of that X start. All right. And then we switch on that alignment value. And here we blit SSE destination aligned. So this means that it's already going to be aligned, that the destination is going to be aligned. And so our job will be easier. Otherwise, if the destination is not going to be aligned, then we're going to have to do a little bit more work. So let's look at the destination aligned part here. Now I'm kind of glossing. I'm not going into super detail. I'm not going to draw diagrams for every single little thing. So if you are interested at all in knowing more about some stuff that doesn't make any sense to you, feel free to ask any questions you need, and I will always be around to answer what you need to know. But to continue on, so here is where the destination is going to be aligned during our transfer. So in this case, what we're going to do is, first off, we're going to peel we're going to peel off the part of our source that is not aligned. So this is the loop peeling part that I was talking about in the beginning. We use loop peeling to correct our source alignment, and then we use the pump priming to correct our destination alignment. Now, this calculation here told us that after we peel the loop, the destination is going to be aligned. So we peel the loop, and now that we've peeled the source and the destination are aligned, and so we just call source destination aligned, which is just a very simple copying of values without any further bullshit. And then we peel the loop on the end if necessary, and then we're done. So that's the simple situation where after we do the loop peeling, this is the calculation to find the destination X after the loop peeling is done. And after we do the loop peeling, the alignment is 0. It's perfectly aligned. Now, if after we do the loop peeling, the alignment is not 0, then we're going to have to do our dumb bullshit with the priming of the pump and so forth. So we go here. Again, we peel the loop. We peel the parts of the source that aren't aligned. And then we call our row template function for the alignment here. And this is the same thing I showed you before. This is just where you prime the pump and then you do your alignment and all your fun bullshit, and Bob's your uncle. And that's it. That is basically it. Yes. So this part is basically the same as we had before. You've got your SSE template function, which contains your while loop, and which calls your row template function, which contains your X loop using pointer arithmetic. And it primes the pump with the destination values that won't be overwritten. And at the end, it finishes off the last section that contains destination pixels that will not be overwritten, using, again, the shifting and masking bullshit that I talked about before. And there you have it. That is all there is to be written about this function here. So let me take a look here. Where are we at? Where are we at? This one here, blit SSE. Now, blit SSE 3 is the exact same thing, only for the shifting and the masking, it uses the p-align r instruction instead of, you know, shifting and masking. So it's a little faster. It's going to be a little bit faster than your other one. Let's just take a look at that for a second here. So let's make some comparisons. So I've got a little function. A little function called, what is it called? It's called make blit batch, and it just makes a bunch of rectangles and points for blits that blit to the screen, and it does such that there's no clipping involved, because our functions so far they don't take into account clipping. So what we're gonna do, we're gonna get rid of this draw rect, and we're gonna go. What are we gonna do? What are we gonna do? So let's try blit. So we'll try our standard blit, and we'll see how long it does, how long it takes. The actual job, the vector of blit jobs that is created, we'll use you can specify in this function, you can specify a seed, and since 420 was exactly 4 days ago, I think it's a good number to use right now. Blaze it, 420. Is that a meme? Am I a memer? I'm a memer. I'm a schemer. I'm a Monday morning dreamer. That was a good rhyme. I hope you enjoyed. Oh, okay, yeah, that's fine. So here's our blitz. I don't know how many rectangles I've actually put in this blit job, but I can check up here. Where is it? 20. Let's up the ante just a little bit here. Let's go for 60 rectangles. We'll get a nice nice sample size here. So here's what it looks like. This is blitting using just a standard algorithm, and it gives us, wow. Okay, so it takes a long time, and that is why. Oh, and also we're in debug, which is probably not a good idea for doing a performance test. Just saying is all. So here's our stuff. We'll let it run for just a couple of seconds, and then we'll stop it. Check the log file. So yeah, we've got about 1.9-ish, 1.9 milliseconds. And let's try with blit SSE. Let it run for a little bit. And we'll check the log file. So 1.4. So you get a decent speed increase, but it's not huge. It's not like many times faster or anything. And the reason for that is, I mean, in general, just blitting, just copying to the memory is going to be fast. There's really no computation going on behind the scenes there. So you can't expect a huge speed increase in this situation. But you get a decent increase, if you know, like 30% or something. I don't know how much you get, 20%, 30%, whatever. You get some increase here. Now, what is interesting to note is blit SSE is going to be considerably faster when the source and the destination are aligned. So if you're copying from aligned portions and you're also copying two aligned portions of memory, you're going to get a lot of better increase. Whereas the standard blit, there's no difference there. Now, we can use Blit SSE3. So this one was giving us what? It's kind of all over the place, but let's say in general 1.5, 1.5-ish, 1.55, somewhere around that region. If we try to do with Blit SSE3, take a look at that. Yeah, we'll reload that. Now you've got like 1.4, 1.4 something. You get a little bit of an increase. Nothing to write home about, but shaves maybe 10% off of your runtime by using the PLINR instruction. A little bit of a boost. Nothing to write home about. Let's take a look at something else here. Now is the time where I let the cat out of the bag, basically, because there are instructions for SSE that allow you to load and store from unaligned addresses that are not aligned. And these ones, I mean, obviously you don't have to do any alignment bullshit for them, except at the end, if the last number of pixels that you have is not 4, then you're going to have to copy them individually or do something else. Right? But if your width is a multiple of 4, you don't have to do anything special. You just load and store and you're done. So that is obviously a lot easier. I mean, look at all the bullshit we had to go through here. We've got a function to handle just standard if it's just less than 4 pixels wide. We've got a function here to handle if the alignment, the source is already pre-aligned. And then we've got a function here to handle if the destination is always already pre-aligned. And then we've got a function here, a template function, that calls another template function that does a bunch of dumb bullshit to align our bullshit. And that is obviously a big pain in the ass compared to this. This calls no other functions, it's just everything is right in here. Well, except for the case where you have less than 4 pixels. Obviously that's a special case. But outside of that, this is super simple. So, the question is, why wouldn't you always use this? Why would you ever use anything but this? And the answer is in general, loading and storing from unaligned addresses is slower than doing it from aligned addresses. Now, here's the thing. Back in the day, back with older CPUs, like for example, let's say even like a Core 2, there would be a very large penalty for using store U and load U. And the penalty would be so great that it's basically, you shouldn't use them ever. You should always try to align the addresses yourself and then use the standard store and load. But in recent years, I think starting with maybe Ivy Bridge or I don't know what architecture, Intel made the logic for store U and load U much better. So now, in general, from what I can see, compared to fixing up yourself, store U and load U actually faster. Not just like the same or a little slower. It's actually faster. So let's look at this SSE3 thing. We've got about, what, 1.45 maybe? It's all over the place, but let's just say 1.45 for the record. Now let's go Blit SSEU. Build that. Let it run for a couple seconds. Yeah, I do want to reload it. And now we're down to 1.3, 1.4-ish. It's all over the place, but in general, I'd say 1.3. So for all of the work that we took, it's still faster to take the easy way out and use this. But the thing is, that was not always the case. So the question is, what CPU are you coding for? If you're coding for an older CPU, then you should probably do all this bullshit if you want to get the maximum performance. But if you're coding for a newer CPU, then doing this bullshit is actually a little bit slower than taking the easy way out. So that is one question that you're going to have to ask yourself. Now, the optimum solution here, the best thing you would want to do is code both, and when the program starts or when the program installs in the first start, you run a benchmark, check to see which is faster, and then you write in a configuration file, use unaligned blit or use aligned blit or whatever. That is the optimum solution. But I mean, that's a huge pain in the ass. So probably, newer CPUs, they're probably not going to go back to the old way of doing things. So it's probably, unaligned access is probably not going to get slow again. But it depends. The thing is the question is, what is your motivation for writing these optimized routines? If your motivation for writing optimized routines is to allow the greatest number of people to enjoy your game, then you want to focus on the people with the shittiest hardware for your optimization, because you want to bring them up. Focusing on the people who already have newer CPUs is it's a win more situation. It's giving the winners just a bigger win, but it's not bringing the losers up anymore. So there's a philosophy in that. The best thing to do would be to write both algorithms and then benchmark them at runtime. But like I said, that's a big pain in the ass. And what I'm thinking is that these days, the CPUs that have the slow unaligned access, they're getting fewer and fewer. So you could probably forget about them. Now, I don't know about people with, like, for example, Intel Atom processors, or, low-end Celeron grade processors, or even like i3. I don't know where the cutoff is. You'd have to look into that yourself. But all I know is that in the higher end CPUs, the mid to high end range, CPUs that can't do unaligned fast are getting fewer and fewer. So you have to look into that yourself. You got to weigh all of the different variables to decide what algorithms you're going to put in, how much effort you need to put in. But if you're looking at this and you're saying, I am not going to do all this bullshit, then you might as well just do this one, because it'll give you a speed up in either case. And in most cases, it's just going to get better as time goes on and people keep ditching their old ass CPUs. So that is my tirade about, the CPU architecture evolutions and whatever. Now, there is one thing that we can do here. And the thing is, here we're doing unaligned stores and unaligned loads. And at the end, we're using, loop peeling to fix up the last few pixels that didn't fit into a full SSE load store. Now, we can do better than this. Just because we use the unaligned addresses doesn't mean that alignment doesn't matter. Unaligned is still going to be faster. This instruction here is still going to be faster if we do it from an aligned address rather than an unaligned. If we do it from an aligned address, it's going to be the same speed as this thing here. It'll be the same speed as this. But in an unaligned address, it's going to be slower. That doesn't change. So what we can do, remember the whole problem was that our source and our destination were out of phase with each other. We didn't have that problem when we only had to deal with a destination. And the same thing is true for our blitting. All we need to do, really, is use unaligned on one of either the source or the destination, and then we can use aligned on the other. So instead of just saying, fuck it, I don't care, just do unaligned with everything, we put a little bit of work in. We make it so that, well, for example, in this function, the destination is aligned. So this is an unaligned blit, but the destination is aligned. So we do loop peeling at the beginning and at the end to handle the parts of the destination that aren't aligned. And in the loop here, in the main loop, we only do aligned stores to the destination, but our loads are unaligned. And in that case, let's take a look at our speed. So here, destination is aligned. So for both unaligned, we're getting about I don't know what to call this. Let's just call this 1.336. 1.36, remember that number. SSE destination aligned. Build. We run that. Stop it. So that was 1.36, right? Now we'll go to log file. We're down even better. 1.241, 1.24. So by aligning to the destination, we have improved our lot in life. Now we can do the same thing, but we can align to the source. Let's just take a look at what we had here. Let's say this is 1.28. So now we'll go source align. Remember, we can't align both. It's not going to work. But we can get one or the other. So we had 1.28 before. Now what do we get? 1.3738, 1.4. So it looks like for this one, is this source aligned? I'm a little bit confused now. I'm going to definition. Store unaligned. Yeah, source is aligned in this one. So it seems like destination aligned is better. Now it'll depend on your situation, which is going to be faster. I'm actually a little surprised with this result, but whatever. I don't want to make this video too long, so I'm not going to go into the details. But basically, either way, aligning one of them is better than just saying fuck it and not aligning anything. All right. Now the last thing that I want to talk about here in this video is we're going to do the same thing, but we're not going to do blitting. We're going to be doing alpha blitting. So we're going to use the alpha algorithms that we developed up here in the full screen filters, but we're going to be applying them to the blitting. So again, we can try it with source and destination. Here is basically just the blitting stuff here. And I'm using the SSE3 version, so that uses the P-shuff-B, the shuffle here, to do the unpacking and the broadcasting of the alpha channels. And yeah, that's just the blending part. I create a lambda function to handle the blending, and then I call that lambda function down in here. Now, for the what is it called? The loop peeling, I just use the standard, what do you call it? Not vector, but scalar alpha blending function here. I could have created a separate function, but I just instead copied and pasted this, which is probably not a good idea, but I was feeling lazy at the time. All right, so yeah, we just do the same basic thing, only we use blending we blend. So we got to load the destination and the source, blend them together, and then we store them back in the destination. And you've got a source version, you got a destination version. One is faster than the other. I believe doing it with the destination aligned is faster in this case as well. It surprised me that it was faster in this case, but this case it makes sense that it's faster. Destination, because you've got to load from the destination to do the blend, and then you've got to store back to it. So it's a good idea. The thing you're going to do, load, store, make that thing the aligned thing. And so that's all there is to this. It's basically just the same as the blitting, only you've got the alpha blending stuff built in there. And just for completion's sake, I did the aligned algorithm, but for blit alpha, which caused me to have to rewrite all that bullshit up there, only with alpha pre-multiplied versions. And that, let me just say, that was a pain in the ass. But it's basically the same as what you have before, except for maybe one or two little differences. And let me just check here. Alpha pre-multiplied, source aligned row template. We're getting into the long function names now, friends. Go to definition here. Yeah, this was a little tricky. I think the tricky part was, for me, figuring out that when you prime the pump, you can't just load the destination and then put them together and then store, because you're doing a blend operation in the main thing here. So to prime the pump, we actually prime it just with transparent pixels. And doing that means that the parts, the beginning of this loop here, is not going to write those pixels to the source. So it's just going to keep the source. But otherwise, it's basically just the same. And I do a little trick here. FF, in our case, because when we pre-multiply, the alpha value is actually the alpha complement. And so FF means that take all of the destination, none of the source. Now to load FF into all the alpha, and we just load it into every pixel value, we can use a trick by comparing a value to itself, that the result of that is just all ones, because when you compare anything to itself, it's going to be equal. And when the values are equal, it just puts all ones in the destination register. The corresponding position in the destination becomes all ones when the values are equal. So we do that trick. We compare a value to itself. Just any value is okay. And doing that will give us a value that's just all ones. And we won't have to load from memory. And that's just a little bit faster. It's just a little trick of programming. Just like if you want to zero out a value, you exclusive OR the value with itself. This is to put all ones in the value, all binary ones. So, but that's all you got here. So this part is a little different than in the blitting version, but otherwise pretty much the same. But it took me a while to debug all this bullshit. It was an enormous pain in the ass for really no gain, because I mean there's certain situations where you'd want to use this one, but basically not this one. Where is it? Where you'd want to use this one. But basically you're going to want to use one of these, probably this one. So let's compare blit alpha pre-multiplied with all of the blit alpha. I believe that is the name. No, that is not the name of the function. Okay, well, fuck me, I guess then. Blit Alpha pre-multiplied packed is the correct name of the function, apparently. This is just a standard one, with a little bit of optimization, but no SSE. So we'll build that. Now we're doing alpha blending. So there you go. We'll let it run for just a little bit, and we'll take a look at the times. Now, this is obviously a lot slower than just a standard blit because we're doing a bunch of calculation. So here we've got basically, what, 9? I'm seeing about 9 here. We'll just say 9 milliseconds. And now let's take a look at the blit alpha pre-multiplied. I'll just delete all this. It's faster. Blit alpha pre-multiplied. That's blend. We want blit. Alpha pre-multiplied. Destination aligned. There we go. This is probably, I believe, the fastest one we have. So the non-SSE gave us 9 milliseconds. SSE gives us 1.92, gives us about 2 milliseconds. So, we're over 3 times faster now. And that is, that is the kind of speed increase that we would expect from SSE. We didn't get the much increase with the blitting because there wasn't much calculation involved. It was just moving the memory. The bottleneck was the memory. Here, the bottleneck becomes the calculation. And thus, SSE gets a huge advantage. So that was about 2 milliseconds. Let's try with our aligned version. See what we get. I'm guessing it's going to be somewhat slower. 10%, 20%, I don't know. 2.1, 2.2. So yeah, you're getting, between 5 and 10% slower maybe. Maybe like 7% slower. I don't know what the numbers are. But it's a little bit slower if you do it yourself rather than you let the unaligned axis instruction do the alignment for you. And just for completion's sake, these functions are fine, but if you try to draw off the edge of the screen, you're going to get fucked. So what you want to do, and this is easy. This is not what I wanted to look at. I want to go to surface. What you want to do is you want to pick one of these functions and you want to clip, you want to adjust the source rectangle and the destination point such that you're going to be drawing within the region specified by your clipping rectangle. So you can just do a few quick tests and adjustments here. I'm not going to explain this. I've covered this before. And then you call the unclipped version of the function, and Bob is your uncle. And that works. I've tested this function out. I could quickly go over here, and where's the here? And I could go make blit batch 2. This one generates blit commands or blit data that goes off the screen. And by doing so, and by going into here and going, let's just go back here. Blit. And where's the clipping one? There's gotta be a clip one here. Blit alpha pre-multiplied destination unaligned destination aligned clip. Not too long at all. Perfect length for a function name. There we go. Clipping. Add the clipping rectangle there. And start without debugging. And there you go. You've got rectangles which appear to be going off the screen. We can't, tell exactly whether they are or not, but they probably are. And we'll stop that. Take a look at the log file. The values are lower because obviously we're not going to be drawing all of the rectangles that we were before. We're just drawing portions of them because some of them are going off the screen. But you get the idea. This is the end result of something that you could use in an actual game if you were using, you were limiting yourself to not using the graphics card to draw, which you normally wouldn't. But like I said before when I started this, these functions, are not meant in general to be used in a game engine. You could use them and they're very fast, but they can't beat what the actual graphics card would be doing by just firing triangles onto the screen, textured triangles. So the main reason why I did all this bullshit was just to teach people how to use SSE, because there's not a lot of material on the internet about this and on YouTube. No explanations on how to actually realize real functions in SSE. And that's why I did that. And that's why I talked about this alignment bullshit, because it's important, even though it is an incredible pain in the ass. And even though you have access to those unaligned stores and loads, and you could basically ignore all the bullshit that I talked about, you still get the best performance by trying to do your best job and aligning at least one part of your data processing bullshit. So that's why I talked about it. I did the job. I did the hard thing. Even though I wanted to do the easy thing, I did the hard thing, and I feel better for it. And you will feel better for it too. But that is all we have for today. And basically, this is everything I needed to teach so that I could talk about the blending, the Bloom algorithm that we're going to be using in the Hugs series. So the optimized Bloom is going to be using SSE, and it's basically going to be using all of the stuff that I've taught up until this lesson. Now, I think I'm going to do one more lesson about integer SSE, and that's going to be about masking and branching. It's going to be a little bit about SSE and a little bit about branch prediction and how the CPU does that. And that'll be the last thing I talk about in integer SSE. But I might do more SSE after that, but it'll be, it won't be integer, it'll be floating point stuff, which is also incredibly useful. Probably more common to do floating point SSE than to do integer. The reason why I wanted to tackle integer was because you don't see much information about it on the internet. It's a much less common skill that people have. So that's why I tackled it first. But yeah, so next hand relief episode will be about branching, and especially branching and how it relates to SSE. And after that, maybe some floating point stuff. We'll see. We will see. But until then, I'm Chili signing off, and I will see you in the next Hugs episode, I guess. Ta-ta.